All right, good morning, everyone. Welcome to day 4 of the Mars Society Conference. Our first speaker is coming right up. Just give me a moment and I'm gonna read her bio. Okay, awesome. We're gonna go ahead and get started now. Our first speaker this morning is Dr. Jingnan Gao from the University of Hong Kong. I'm sorry, from the University of Science and Technology of China. My apologies. We're ready to go now. Thank you so much.
Can you hear me well?
Yes, we can hear you just fine.
That's great, because for me, your sound is breaking up a bit. I'm wondering if it's okay.
You're coming through loud and clear.
Okay, that's great. So, hello everyone for being here and being online. So this talk I'm going to give today is the radiation environment and how it challenges future human explorations for the red planet. I'm Jingnan Gao. As introduced, I'm from the University of Science and Technology of China. This work has been a lot of collaboration with the University of Kew, where I stayed for 9 years in my career. It's a great honor for me to be here. I'm really honored. We know that the future steps and goals for human space exploration is to go to Mars. This is the goal of NASA as well as some other space agencies. Some recent and upcoming plans for exploring Mars include, exploring the habitability and prepare for human explorers seeking for life and so on. Only about 10 years ago, most of the missions were from ESA and NASA, ESA and NASA, but we know that in the last couple of years only, there are many India, China, and other UAE Mars missions. China's Tianwen-1 orbiter, lander, and rover is a package of a Mars mission. Arrived a couple of years ago and has been exploring Mars for the first time. And in the future, we're talking about sample returns. We know that following Mars 2020, there will be a series of NASA sample return missions. And Tianwen, we also have its planned sample return missions around the year 2028. So there's really a lot going on to the red planet from different international agencies. Talking about habitability, one of the important factor is radiation. We know that for astronauts, there could be happening a lot of risks for their bodies in space for their health conditions. And the main things are basically radiation and lack of gravity. So whatever happens to them in space is from these two factors, or the combination of them. And talking about radiation is really one of the things that is very difficult to shield. This I will talk about later. And for a mission to Mars, which involve about 1 year of international travel, interplanetary travel, and more than 1 year of stay on Mars, radiation is a big factor here. This is a chart that summarizes the different risks of health for humans in space, both during and after the mission, and radiation is really one factor that influences the astronauts even after the mission, influence their health, causing long-term cancer and so on. We are generally talking about two types of radiation in space, galactic cosmic rays and solar energetic particles. So galactic cosmic rays, they come from outside the solar system, such as accelerated by big shocks during the supernova explosions. And by the time they reach the solar system, they are kind of omnipresent in the low intensity flux. but they have a very wide energy range distribution up to more than TeV and so on, and peak around GeV. GeV proton is having energy about 0.9 speed of light, with the speed of light velocity. Solar energetic particles, on the other hand, they origin from the sun during the solar explosions. They can be accelerated by flares and shocks related to CMEs. So they are more frequent during solar maximum periods and less frequent when the sun is less active. And they mainly accelerate protons and also helium ions and electrons with energy that is generally lower than GCR, but they are also very impacting on space missions. So this is one of the most exciting image we have gained in space. Is from the Voyager 2 spacecraft. It measured these energetic particles seen at the edge of the solar system. We know that the Voyager missions were launched in 1977, and after decades of flying in the interplanetary space, Voyager 1 left the solar system in 2012, where Voyager 2 left about 6 years later. And one of the very great proof to show that, okay, they left the solar system is to really see the decrease of the heliospheric particles on the edge of the solar system, where the galactic cosmic rays increases very suddenly during this period. This was a very good proof that they left the solar system. So this shows how the particles origin. Galactic cosmic rays, GCRs from outside the system, they come inside. So that's why the influx is higher outside the solar system. Heliospheric particles, on the other hand, they origin from the sun. So in the inner heliosphere, that we're getting closer to the sun, we're talking about Earth and Mars orbit. The main drive of the solar varying radiation condition is the solar eruption. So the flares can accelerate particles in process such as magnetic reconnection. CMEs, on the other hand, they are like the big plasma blob thrown out from the sun. During these eruptions can also drive the shock that further accelerate particles into space. We know that the charged particles, due to the Lorentz force, they gyrate along the magnetic field lines. And the magnetic field lines in space, they are not straight outward. So these particles can gyrate easily along the magnetic field line, and they can reach us depending on how we are connected magnetically to the source of the particle. This is a plot I made that shows more than 4 solar cycles of sunspot number on top, solar cycle 21 to 24. And the lower part shows the GOES spacecraft measuring different energies of particles in space. We know that during the solar maximum, where the sunspot number is large, we're looking at more SCP events, that is plotted in as impulsive events here. And the long-term background instead is anti-correlated with the sunspot number. At least in this plot you see this kind of a slow varying background. Those are mostly GCR particles. So we see a background, and on top of which we have the solar eruptions. These are the main particles that drive the inner heliosphere radiation environment, also including Mars. This measurement is, however, measured near Earth. So we know that Earth has the magnetic field protection and also has a very thick atmosphere. But when we talk about Mars, Mars does not have an intrinsic magnetic field to protect high energy particles reaching it. And its atmosphere is also very thin. So Mars is more exposed to these high energy particles, which can more easily go to the surface of Mars, where astronauts in the future will stay. The first detection of the radiation on Mars come from the NASA Curiosity rover, which landed on Mars in 2012. This is a nice picture of the rover with a selfie. And the instrument I'm going to talk about in this talk is the radiation assessment detector, RAD. It measures both charged particles and neutral particles using different detection techniques, which I'm not going to go into the detail. Only one thing I'm going to talk is the dose rates that you may want to know that the dose rate is energy deposited by all particles in per mass of the detector per unit of time. And that's a very important measure for radiation. This is a summary plot of the background GCRs and SEP measured on Mars since 2012 until lately. We see that there are a few very important SEP events on the surface of Mars. There are not as many as there should be because solar cycle 24 is one of the weakest in the space age. And the background GCR slowly enhanced towards the deep solar minimum of solar cycle 24 and peaked around 2021. So we're really looking at the surface Mars radiation environment measured by the RAD-E dose detector here. And this is solar minimum of the past solar cycle 24. I'm talking about that the GCR reached the peak. Let's briefly look at the last two solar events, which are the biggest so far. The fifth event happened in 2017 September, and this is the two different detectors, B and E, measuring the dose rate. So B is on top, and it measures a higher SEP event flux compared to the E background, which with the numbers written here. This basically means that the SEP particles they can penetrate more, they can deposit more energy at the surface layer, but not deep into the body organs. So we may expect more skin dose compared to the organ dose when the SEP events occur on the surface of Mars. Similarly, we have also B higher dose than E in the other events. And the second event has a higher flux, peak flux, but the total duration is shorter. So it also has a smaller integrated dose. So this is when we're talking about the dose rates, that is the derivative time. You may have different evolution in time when you're talking about different events. This is the work, this is animation based on our work analyzing different radiation in space. So Earth is here, Mars is here, and there's another spacecraft called Stellar A that is also on the backside of the sun. As you can see that when there's a CME eruption, and it was mainly towards Mars, this red blob here, the plasma blob. We're talking about, okay, this coming one here is erupted towards Mars. But the SEP was much more, has a higher flux near Earth. So this is mainly because CMEs and particles, they travel along different paths in space. Mars has also a ground level event here, and Earth actually also had a ground level event. A ground level event at Earth means the particle had energy up to more than a few hundred MeV, so that the particles can penetrate through the atmosphere and somehow trigger the ground level neutron monitors that recorded the secondary particles generated in the Earth's atmosphere. So this is the first ground level event ever observed on two different planets, Earth and Mars. So we were all very exciting about it, but we can, after careful analysis, we know that this event was very different at two different planets. And if we talk about the GCR background, we actually already said that towards the solar minimum, the GCR went up. That's because the sun, the solar heliosphere, is like an umbrella shielding us against the incoming galactic cosmic rays. So when the solar activity is weaker, we have a stronger GCR background. Actually, we also have some diurnal variation in the data that we see that varies with day and night. That's the atmospheric change and seasonal change, about 20%, and some Fallbush decreases. These are because when you only have a CME happening, not SEP accompanying the CME. When you have the CMEs happening, reaching Mars, you can have a temporary shielding against the GCRs, and then you see the decreases in the data. And there are also some surface shielding, like when you're next to the cliff. And we also observe 20% of the albedo contribution. These are the particles reaching the surface, they backscatter from the soil, and then they come up again to contribute to the radiation. And that's been derived to be about 20% on Mars. So you not only need to consider the radiation downwards from space, but you also need to consider there's some deflection from soil. Talking about heliospheric modulation, there's a long-term solar cycle dependence. We already saw this in our data, the 11-year solar cycle that is anti-correlating the GCR and the solar sensible number. Here we're also talking about short-term Phobos decreases, and this I already introduced. That's when the CME happens and the particles are temporarily deflected. Like here, we see the Earth and then Mars. So this is because the structure first arrived Earth, we saw the Phobos decrease, and then they arrived at Mars about 1 day later, then you see it again. The long-term changes due to solar cycle evolution is also plotted again here. So this is not sensible number, but something similar, describing the solar activity is called the potential modulation potential phi. You can see that it's perfectly anti-correlated with the Mars dose we measure on the surface, and the increase of about 50%. This you can quantify it with this correlation, and so you can obtain this the relation between these two parameters and use one to predict the other. And this is what we did for the last few solar cycles. Plotted here. So we don't have measurement, of course, since 1960s on Mars, but use the known parameter of the modulation phi and their correlation between the dose rate and phi that we obtained in this period. We can back predict in the last 5 solar cycles what should have been on Mars if we had the measurement, or if we had the dose rate. So this is plotted here. This is mainly the GCR, because for SCPs it's much more difficult to predict. We do not have SCP measurement at Mars. We have at Earth, but it's different at Mars. So this is the GCR dose rate and another quantity called dose equivalent rate. This is a kind of already converted to take into consideration of dose is not directly the biological impact. So dose equivalent rate is more like the radiation, a step closer to the radiation risk for humans. That is the quantity plotted here with the units of sievert. So here we're talking about microsievert per day. That's the rate. Then with what we derived, we can kind of guess or predict what is the total GCR-induced radiation during a return mission to Mars. We know that the most energy efficient way to go to Mars and come back is to go to the Hohmann-Park transfer orbit. For this, you need to wait for every 26 months. You have a window going to Mars, and you wait a bit on Mars. That is about another year, and you come back. With that, you can, with the relation I got before, you can predict that during solar minimum, the cruise phase radiation, the surface radiation, and for you add them in total, we're talking about 1.6 sievert. And during solar maximum, it's slightly lower. It's only about 0.6 sievert, so less than half of the travel radiation during solar minimum. So if we're talking about background GCR radiation, it's better to go to Mars during the solar maximum. However, we know that there are also constraints, like for the LEO orbit, the NASA just had this discussion, and they decide that an individual astronaut's total career effective dose rate has to be less than 600 millisieverts. So that's 0.6 sievert we're talking about. This is the kind of a new limit. They said before it was about 1 sievert. So if we're talking about our mission to Mars, even if we go during solar maximum, we are reaching the limit here. So that tells you that radiation is still quite a challenge. for future human missions to Mars. Some things still have to be, scientists, engineers have to work together to work out a better mitigation strategy to better shield this radiation on the way to Mars, and maybe also on the surface of Mars. This is just to give you another idea for people who are not too familiar with the unit of radiation. What is a sea level radiation? What is a CT scan? You can see we're talking about really orders of magnitude higher when we're going to Mars. Actually, on the surface of Mars, shielding is quite feasible because we have different structures on Mars. There are cliffs, rocks, and even caves. We even saw this kind of shielding in the data once. So when the rover was going around, searching around, it was once parked near this cliff for about 13 days, or 13 sols. One sol is 1 day on Mars. It saw a decrease about 5% during the parking. You see this background thing here changing. That's the radiation variation due to other factors of solar modulation. And then all of a sudden, it's kind of reached a small, bottom for about 13 days. This was during the parking, and it was only for 5%. Okay, then it's not a lot of shielding at that moment, but we know that, okay, using a structure, we can do some shielding. And then we can follow the idea and do more modeling work. So this is one of the modeling work we did lately. So we are looking at the height on Mars from 0 to 70 kilometers above the surface, and also beneath the surface from up to 10 meters here. This is log scale beneath the surface. You have to be careful reading the numbers here. And we model different scenarios, including solar maximum, solar average, so solar activity average years, and solar minimum years. You can see that different lines represent different locations on Mars, because we have different locations on Mars with different pressure. On top of Mount Olympus, we have very thin atmosphere, but inside some craters, the atmosphere is much thicker. So the radiation can change because you have different atmosphere thickness. And of course, it also depends on the solar activity cycle. And when you're talking about shielding with limit about 50 millisievert per year or 100 millisievert per year, if you want to keep the radiation below these levels, you have to dig. You have to dig a bit into the soil, or you find some structures that has this kind of thickness. And when we are talking about this kind of digging to protect future astronauts against radiation, we're talking about above 1 meter of shielding. If you dig not thick enough, you might even reach a higher radiation exposure for astronauts on Mars. That is because the particles can further interact. After interacting with the atmosphere, they can further interact with the soil and generate a lot of secondaries. And these secondary particles can contribute to the radiation as well. This includes very dangerous neutrons. We call them dangerous because neutrons, they don't feel the magnetic field. So they don't interact with matter like charged particles. So neutrons can be very problematic for future astronauts on Mars. So these secondary particles cause a peak underneath the surface. So you have to dig really a bit more to further reduce the radiation on Mars. Okay, so we have really varying Mars radiation environment for manned missions to Mars. We talk about over the long term, the Martian surface radiation is modulated by solar cycle dependent heliospheric magnetic field strands that varies up with a 11-year solar cycle. And at different time scales in the shorter term, there are dynamic variations in the radiation field on Mars, reflecting the changing heliospheric, planetary, and other local topographical features. The variation in the Martian radiation field is mainly caused by these factors: the atmospheric change, daily change, and seasonal change. There was no time to go into the details in this talk, but if you're interested, I can give you some references later. There are also the heliospheric influence, both in the long term and in the short term. In the short term, we're talking about SCPs. We saw some events on Mars we will surely have more events in the future. And also even when astronauts are there will be events, we have to do warnings for them. And actually there were also voltage decreases. So this is the temporary shielding of the background. So we see a decrease. And the topographical change along the rover path, we saw that shielding effects. And the quantification of the variation of the radiation fields using the data so far helped us to understand the Martian radiation fields and to make better plans for mitigating radiation for future human exploration to the red planet and the different conditions. At least now we know that it's anti-intuition. It's not during the solar maximum, but maybe during the solar, it's not during the solar maximum that there are more radiation, but during the solar minimum, we have more radiation because the GCR background is very high during the solar minimum, and they are very difficult to shield because they have very high energies. So if you want to go to Mars with a reduced background radiation, it's better to do so during solar maximum. And during solar maximum, there are more SCPs. So we have to be more careful, better predict and reduce the radiation risk by SCPs. That is a very important task for both the engineers and solar and heliospheric physicists. Okay, these are the references I have, and if you're interested, you can look into them for more details. That's all what I have. Thank you very much for your attention. I don't hear anything. So I have a question here. How do those radiation measurements compare with those seen by the Tianwen-1 rover? This is a very interesting question. We don't have the Tianwen-1 rover. We do have the Tianwen-1 orbiter that measures the radiation orbiting Mars. However, it doesn't measure the dose rate, so we cannot do a direct comparison here. There's another orbiter called the TGO, so that's the ESA mission. The TGO orbiter orbiting Mars has the radiation dose rate measurement, and that value, if we're just talking about dose rate, that's about double the surface measurement, about double. So on the surface, we have about half of the orbital radiation. And a simple way to understand is kind of easy because, on top of atmosphere, you don't have that much of the atmospheric shielding. So you have more radiation orbiting Mars. Actually, probably it's not around double, but slightly higher, not yet double. Sorry.
Thank you. We do have a question for you.
Question.
Just a moment.
Okay.
My question is about the ability to predict and protect against a major coronal mass ejection like the Carrington event in 1859.
Yeah.
What, if anything, do we know how to predict those? Is it like earthquakes where you can see the pressure building up in a fault? You don't know when exactly it's going to release, but you know it's probably going to come soon. Or is it other processes we don't understand yet? And also protection, is it because it lasts such a short time that you don't really have to worry about it too much because the cumulative exposure is not that much, or you still have to worry about it having shelters with extra protection in case you get a super event that's an order of magnitude bigger than a normal CME?
Thank you for the question. It's a very good question. That question can be asked to the whole community of the solar physicists and heliospheric physicists. It's very challenging to do really like a week ahead prediction. Right now we can do maybe hours ahead using also some nowcasting tools. So you're watching the sun, you see something's coming up, the flare explosion, and then you work out, okay, how long it takes for particles to travel out, how long it takes for this radiation to go up. I think future astronauts, especially for deep space missions, will surely carry dosimeter or particle detectors with them. So when they start seeing this kind of enhancement of the flux, they can go to some shelters, as you already mentioned. So the shelters will be necessary, but it serves mainly for SCPs, because for SCP it could work. SCPs normally have energy range much lower than GCRs, up to a few hundred MeV. So you can try to shield against them. Something like 20 centimeter equivalent thickness of water, for example. Water you carried along with you anyway on their way for deep space missions. So you can use this kind of shelter or some jackets to shield the major organs. So forecasting will be needed, but it's challenging days ahead. Nowcasting is surely will be important, and the temporal shielding will be very, very useful against SCPs. I hope that is a little bit helpful. Thank you.
Thank you so much, Dr. Gao. Thank you. Okay. Our next speaker is Dr. Maria Perino from Thales Aerospace. Maria, are you ready to present? Maria, can you say something?
Yes, I'm ready.
Awesome. Thank you so much. Okay,
Good morning,
we have you
everybody.
spotlighted.
Can you
may
see my
begin.
screen?
We can see your PowerPoint, but it is in the edit mode, not the presenter mode.
Now, better?
That's better. Thank you so much.
The voice is okay?
I'm sorry, say again, please.
Can you hear me fine?
Yes, we can. Thank you.
Okay, good morning, everybody, and thanks for inviting me to speak at this conference. I really need to thank the previous speaker. Fantastic presentation, and I hope I can contribute to the discussion by sharing with you what our company, Thales Aerospace in Torino, in Italy, what we are doing precisely to design and manufacture space habitat where people, for deep space, where people can live in a comfortable but also safe environment. Let me move. Next slide is not moving. Yes, the starting point for us, and I shall say for all mankind, the starting point for exploration is in fact the International Space Station that is orbiting above our heads, 400 kilometers daily. Beautiful laboratory where in fact we are learning how to live and work in a very hostile environment that was just described a few minutes ago. So why is so important the International Space Station? To prepare us for explore further away moon, around moon, and in transit to Mars. Because in this laboratory we learn many things. We learn how to deal, for example, with the radiations, how to deal with the fact that we will experience a different gravity environment that will affect our body, for example. So this lesson learned will be instrumental for us to further move. It's important also from a technological point of view, because we have the possibility to validate there what we will use for Moon and Mars. New structure, lighter, more modular system. We will need to regenerate our resources, for example, for life support. And so, in fact, the International Space Station is a sort of in-space test bench where we can complement what we are doing R&D on ground. And then the key, another key aspect, so not only the physical aspect, not only the technical aspect, but especially the psychological aspect. How human will live in a different environment is still an understanding gap that we need to fill. I I love this picture because it shows the Italian contribution to the International Space Station. I don't want to take your time in going through the different pressurized elements, but this is indeed what we are able to do. We are able to build a pressurized module for people to live in space. Just let me mention one, Cupola is our Julia, really, is the place where people love to spend time, because from there they can see Earth and they can feel that they are not too far away. And that will change, because when they will be looking at the Earth from Moon, and even more so from Mars, well, the feeling will be different. They will feel how far they are going to be. In these days, in addition to the International Space Station, in fact, we are designing, and in fact, we are welding modules for the new commercial space station that will orbit around our planet in the next years. We are very proud of that. We are involved in different business project. What I show here is the Axiom Space Station that will be again a scientific and technological laboratory, will be used for astronaut training and also for space tourism. So in fact, space is opening up to, you know, normal people, let me say so. The title of my presentation underlined the point that space exploration, in fact, is a stepwise approach. So we need to move from the first robotic missions that are needed to explore the environment and to provide us with the needed information so that we can design our elements, our building blocks in the proper way. So it's an incremental multi-step approach. And for sure, new systems and technologies are required, and this is precisely what the global exploration roadmap elaborated by the major spacefaring agencies has developed in the last, I would say, 10 years or so. To go back to the moon and to move further toward Mars, we need a different transportation. We need a new powerful transportation system. The new space launch system. In this picture, you see the contribution to this transportation system, that is Orion, and this is in fact the result of a very fruitful collaboration between NASA and ESA. So NASA, we all know, designed the capsule, and the contribution from ESA is the service module that see also our company involved to provide the propulsion system, subsystem, the electrical power, the thermal control, and the consumables. We are all waiting for the first lunar flyby. The Artemis 1 launch without crew is currently planned in a few weeks from now, mid-November. Will be followed by Artemis 2, involving crew, will be a flyby of the moon, and finally the landing on our satellites, hopefully in 2025. In the meantime, we are developing a new orbiting infrastructure, a new orbiting space station, the Gateway, that will be positioned in cislunar orbit. It's not going to be a permanent facility, will be visited by crew for missions lasting 30 days. And again, also for this infrastructure, Thales Alenia Space is busy developing the pressurized elements. In particular, in our facilities, we are welding the primary structure for the first pressurized module. You see that here, Halo. We also got two ESA important contracts for the international habitation and for the Esprit module. The international habitation is similar to Halo, 3-meter diameters. It will have 2 radial ports, but the key points that I like to make this morning is that we are really designing the internal outfit in a completely different way with respect to the internal layout of the International Space Station. The Esprit module was assigned to our company in France. We provide lunar communication, refueling, and cargo capabilities, and will provide a fluid transfer connector between Halo and Esprit itself. Is that difficult? Is that different to design habitats for deep space with respect to the International Space Station? Yes, it is completely different. As the previous speaker, Dr. Guo, rightly mentioned, our planet is really protecting us. We have the magnetic field, we have the Van Allen belt. As soon as we move out, for example, in the vicinity of the moon, we will need to provide more efficient radiation protection. We will need to provide a more comfortable internal layout. So the whole internal architecture has to be human-centered. Dr. Guo mentioned the importance of water to act as a radiation shielding material, and this is perfectly right. We are designing water walls that will be positioned all around the how can I say, cylindrical module. And for the shelter, in fact, we will have a thicker water wall inside. Also from a functional sharing viewpoint, in this view graph, I want to make the point that, in fact, Halo will be, let me say, a more dirty, noisy module with respect to IAB, that is going to be the place where people will find a quiet, cleaner place. So in Halo, they will execute the physical exercise, where in IHAB, we will find the private crew quarters and the social area zones. And this speaks by itself. This is what the astronaut will see when they will look around themselves. So the moon will be so close, they will still be able to see the Earth not too far away, and then I have a view graph. You will understand how different it will be when they will be looking for our planet from the Martian surface. So the gateway, again, you see the Italian flags, will be the result of important collaboration between NASA, ESA. We will have a Japanese important contribution, Canadian important contribution, and many Italian contribution. So we are not only working on the habitation modules, but we are also working on all the major building blocks of the surface infrastructure. In these days, I have to say that we are really focusing on the lunar surface infrastructure. But these building blocks will be essential also to provide an infrastructure for the people visiting Mars in some tens years from now. I don't need to mention all of them, but for sure, ESA is working at the lunar lander. We already mentioned the habitat. We are working at the utilization of local resources, designing rovers, mobility systems, both unpressurized and pressurized. And for sure, greenhouses are important key element to complement the diet of the astronaut, but also from a psychological point of view. They provide in a life system that the astronaut have to care for. So very important. Last but not the least, for sure, the need to develop a telecommunication and navigation infrastructure so that all these elements can communicate between them, among them, but also with the planet Earth on ground. You see here, how can I say, a sketch of the European large logistic lander. First mission currently planned in 2030 will deliver on the lunar surface 1.5 ton payload capability, and there are different missions that we are considering to develop in Europe using this lander. I already mentioned the lunar communication and navigation system, an ongoing activity in our company for the European Space Agency. Let's just have a few words about again, we need to change again the approach for the internal layout of habitat to be positioned on the lunar surface. Why? Because we are no longer in micro G. We have a gravitational environment, is 1.6, but the up and down reality is there. We have to take into account for our design the long thermal excursion on the lunar surface and the excursion, the duration, the long duration of the day with respect to the long duration of the night. So there are, different important key factors to be considered. You see some sketches here of the shelter, of the habitat, and again, people will be there for a few weeks from far away from their family. The environment, the internal layout has to be, they need to feel home somehow. Not only a rigid structure, but also deployable structure. They're important because we can have a big saving during launch. We can launch this pressurized module pack, and then we can deploy and expand them once in position. As Dr. Guo mentioned, we will need to, both for Moon and Mars, we will need to cover this habitat using the local regolith, precisely for radiation protection, but also for thermal control aspects. The mobility system, we consider it a very strategic system because we provide the astronauts with the capability to move away from the outpost and to be able to explore in short-lived environment. Greenhouses, not only theoretical design, but real experimentation. 2 years ago, we brought to Antarctica the Eden project, a small lab that in fact was there for the full winter season and produced a lot of vegetables that were important to complement the diet of the people living there. Some mock-ups, this is really what we have in the company. So it's a beautiful place to work because looks like a science fiction movie, but for us it's reality. This is the Antarctica space station. You see the salad we grow. This is our Martian yard where we test all our rovers and the landing systems. Dr. Guo mentioned before the TGO, the Trace Gas Orbiter, that is currently in orbit around Mars. Well, we were the company realizing it, and so, but I will come to ExoMars in a few minutes. And these are our modules. This is what we do every day. So Artemis is not just the moon, but Artemis is preparing for Mars. And in doing that, in fact, from the Gateway, we learn how to master transportation and the habitability aspect in this space, new protocols. We will need to develop more autonomy because of the long communication delay that the astronaut will experience in transit to Mars and when they will be on Mars. I don't need to further underline the criticality of radiation and so on. There are many learning points that Artemis will provide us. Let me say a few words about ExoMars. ExoMars, in fact, is how can I say, a program involving 2 missions. Thales Alenia Space is the prime contractor of this mission. And a few years ago, in 2016, we launched, as I said, the orbiter, the TGO, that is collecting information about the Martian environment. And the intention was to launch precisely this past September in 2022, the rover platform that in fact is equipped with a drilling system with the capability to drill 2 meters down under the Martian surface, looking for traces of prebiotic life. What happened? And you know, you see here the hardware. So this is the TGO we mentioned before, the lander, the drill. This is the glove box that we use to assemble all the elements to how can I say, to satisfy the planetary protection requirements. What happened? We were ready for launch, and then the historical criticalities that unfortunately are still there now stopped the program, because the program was the result of a collaboration between ESA and Roscosmos. So we are on hold. ESA gave us the request to study a possible launch opportunity. Unfortunately, that will come in 2028, not before. So we might have a rover mission, the ExoMars rover mission in 2030. So we are very sorry in the company. We how can I say, we lost many years. But anyway, we need to maintain a positive attitude. You see, the hardware is ready. We just need to restate the how can I say, the political commitment for this recovery mission that will be subject of the ministerial conference in few weeks from now. Next in the calendar after ExoMars, the Mars Imperator mission. I don't need to tell you what Mars Imperator is. You are a specialist. I just like to inform you about the contribution. We are working with Airbus. Airbus is the industrial lead of the European contribution, let's say, to the mission. And for this system, we are responsible for the communication, the orbit insertion module, and then all the different elements will be integrated in our facility, launch in 2027. Beside the radiation aspect mentioned before, I like to underline the psychological aspect. So the human factor is still a big unknown in deep space. I promised you at the beginning of my presentation that I was going to show with you how different is Earth, the Earth view, when we look at Earth from the International Space Station, when we look at Earth from the Moon, and when people will look at Earth from the Martian surface. So it speaks by itself. The psychological impacts are still to be discovered. So I would say that there are many criticalities for sure. Technical criticalities. Mars is not, around the corner, but all the technical challenges can be, faced and solved. In addition to radiation, we will have to take care of resources. That is not a minor aspect, and physiological aspect and psychological aspect. And soon, this is what we hope we'll be able to see on the Martian surface. And with that, I'd like to close, and I thank you for your attention. If you have any questions or comment, I will be glad to try to answer.
Thank you, Dr. Perino. I think we have time for a couple questions.
Please.
Yes, my name is Doug. If SpaceX demonstrates Starship capability of 100 tons to the lunar surface and perhaps, 100 people to the lunar surface, or even just, private individuals going to lunar orbit, is that capability something that you think ESA is going to have to sort of rework its plans to take into account, to take advantage of that sort of capability? Thank you.
Thank you for the answer, for the questions. It's very interesting. Well, I think that all the entities shall revisit their priorities, taking into account what is happening around us. And space is evolving super fast. This commercial era is not coming. We are fully embedded already. But in any case, we will need the complementary capabilities. So if Elon Musk will be able to bring, so many people in one go all together on the lunar surface, for sure, our company will be super happy to get contracts for housing them on the lunar surface. But complementing the how can I say, the human landing, we will continue to have the need to land on the surface, cargo mission. We will need to land on the lunar surface, scientific payloads, for example. So yes, it's important to not to how can I say, proceed independently, but consider how to, and this is in fact what is happening since I can remember. All the different space agencies come together from time periodically to develop a common roadmap where different nations, entities again, companies, private company, small and big, can contribute. So the roadmap is common. The contributions will be, how can I say, the result of the priorities that the different players may have. I don't know
Any
if I
other questions?
Okay.
We have time for one more question.
Thank you. Great presentation. I wanted to ask about, I really liked your enhancements of the environment in the space station to increase human mental health. And I was thinking of those annoying sounds on the International Space Station, where if a machine is making noise, it can drive you crazy all the way on the other side of the station. Could you expand a little bit on how you would prevent those kinds of noises and smells from going to the other more habitable parts of the station?
Yeah, thank you for these questions. It's very important. We are taking into account, how can I say, needs from all the possible senses. You just mentioned smell, for sure. This is something that we have to take into account. Sounds also, so we are considering material that are, I don't know in English, phono absorbing, and for sure we need to act upfront. So trying to minimize the noise of the different machines that are on board. So again, yes, we consider even the colors, even the lights, the lighting system is part of the equation. So for the internal layout, we collaborate with specialists in different fields.
Okay, thank you so much, Dr. Perino. I think we're going to leave it there. All right, thank you so much.
Thank you.
Okay, I just want to mention, I apologize for not mentioning this before. We had to swap Dr. Perino and Sabina Heinz. So Sabina Heinz is up now. So sorry for any confusion anyone had there. So Sabina, are you ready for your presentation?
Yes.
Okay, awesome. Good to see you.
Can you see it?
I see your presentation in, okay, no, it looks perfect, actually. Yeah, you're good. Okay, let me introduce you. Our next speaker is Sabina Heinz. She's with the Space Renaissance International organization, which is a partner of the Mars Society. I kind of think of them as Mars Society Europe in a way sometimes. They're a pan-European space organization. And Sabina is one of the leadership of that organization, and she's a wonderful artist. She's actually volunteered at our last 3 conventions as a virtual volunteer, and she did a fantastic job this year, as always. She's actually been working all 4 days on all the virtual tracks in that 5th track session we have. Sabina is a rock star, and so I want to thank you publicly, Sabina, for everything you've done for the Mars Society. And you have a full room of people clapping right now. Go ahead with your talk.
Okay. Hello, thank you very much for this very nice introduction. It's my pleasure to speak today at the Mars Society convention. I'm one of the vice presidents of Space Renaissance International, and we're an organization dedicated to civil exploration, exploitation, and settlement of space. Many thanks also to Robert Zubrin for inviting me and encouraging me to speak about art on Mars. This made me want to take a closer look at the topic and brought me closer to the beauty of the red planet in a different way. Today, I would like to pursue the question, is there art on Mars, and why should we bring art to Mars? The Mars has been captivating people for ages, not only scientists, but also many artists felt inspired by him. On this image by David Hardy, Mars is shown as he has seen throughout the ages or times of centuries, and I think it's a very nice representation of technical or technological progress. Talking about scientists, many scientists and scholars have dedicated their lives to Mars. Tycho Brahe cut his teeth on him. And after securing Tycho's data, Kepler set himself the task to determining the exact orbit of Mars once and for all. And he was able to solve the riddle, and Kepler's pioneering laws are still the basis for space travel today. This is a Mars map from 1882, and by the Italian astronomer Giovanni Schiaparelli, observing the canals of Mars. Some of them represent canyons or gradations on in the terrain, but they do not correspond to any structure on the surface of Mars known today. But up until the last century, these observations fueled the legend of extraterrestrials on Mars. Flammarion, also Camille Flammarion, also shows an illustration with the canals in his book, Himmelskunde für das Volk. You can see here the canals in a very nice way, a picture. And while his own observations do not show any canals, as shown here on these pictures, and you can see he did several observations and has not seen any canal on the Mars. Michael Plichter is a traditional globe maker, and he was fascinated by Percival Lowell's spidery map from 1905. And he thinks this might be the craziest map ever made, the Mars Canal map. And it was his dream to have a globe from this map. And since he couldn't get one, he decided to build one of his own. Jack Williamson published the novel Collision Orbit in 1942 under the pseudonym Will Stewart, and in it he formulated the idea of global remodeling of planets by humans and used the term terraforming for the first time. Today, this terminus technicus is in general use and by no means only for the reshaping of Mars and Venus. Here is an artist's impression of the terraforming Mars. In the meantime, the red planet has been better processed than its colleagues, the moon or the depth of the terrestrial seas. A number of missions to reach Mars have already been successful. The Mars helicopter Ingenuity has been on the road for more than a year. He was planned as a technology demonstrator, and now he has major tasks. The Mars rover Curiosity and Perseverance, as well as the Chinese rover Zhurong since May 2021, are also sending permanent images to Earth. Elon Musk, with his company SpaceX, would like to send the first humans to Mars in about 8 or 10 years. The Pristine Beauty of Mars. This is a wonderful book. Unfortunately, it is only available on a really high price. It has many inspirational images taken with a high-rise instrument aboard the Mars Reconnaissance Orbiter. The high-rise instrument shows details of the height and deep depth of the terrain being observed, but in different colors. This is a small selection of some of the spectacular images from this book. I would like to thank you and this to Steve Salmon, another artist, for letting me use this slides to present this artwork. I think you can easily see why he would want to use these as a subject for his own artwork. He extensively sculptured polystyrene for this piece, mounted it on canvas, and then applied common sand and acrylics using dry brushing and shading techniques to bring out the detail. And he used similar techniques for this piece also. And here too, he used the same technique. This lava piece interested me especially. You can see here on the left-hand side lava flows of Mount Etna in Italy, and the 2019 eruption within the context of the last 2 decades. And on the right-hand side, you can see a picture from the book Mars as Art, and this icy new impact. This crater formed in 2008 exposes shallow, clean ice that is not uncommon in the middle to high latitudes on Mars. Sublimation, the process that occurs when a solid changes into a gas without an intermediary liquid stage, creates an ice-free layer on the surface that may be several feet deep, hiding the ice underneath and until exposed by an impact. Noctis landslide. What triggered a Martian landslide? Landslides are common features in canyons on both Earth and Mars, and they happen the same way. Erosion undermines a canyon wall until abruptly millions of tons of rock come crashing down. In the case seen here, the impact of a meteorite landing near the edge of the canyon may have done more than just blast a crater 6.5 kilometers wide. The impact may also have triggered the massive landslide, either at the time of impact or shortly after. The Arabia Dunes, on the right-hand side, the buttered region of Arabia Terra is among the oldest terrain on Mars. A dense patchwork of craters from countless impacts testifies to the landscape's ancient age, dating back millions of years. In eastern Arabia lies an anonymous crater 120 kilometers across. The floor of this crater contains a large exposure of rocky material, a field of dark sand dunes, and numerous patches of what is probably fine-grained sand. The shape of the dunes hints that prevailing winds have come from different directions over the years. This Pfalz color image made from frames taken by the thermal emission imaging system TEMIS about NASA's Mars Odyssey orbiter shows the center of the crater's floor. The image combines a daytime view at visible wavelengths with a nighttime view at infrared heat sensing wavelengths, giving scientists clues to the physical nature of the surface. Fine-grained materials such as dust and the smallest sand particles heat up quickly by day and cool off equally quickly at night. However, coarser materials, bigger sand particles, gravel-hardened sediments, and rocks respond more slowly to the same daily cycle. This means that when TEMIS views these coarse materials late in the Martian night, they appear warmer than the pools and patches of fine-grained sand. In the image here, areas that are cold at night appear in blue tints, while the warmer areas shows in yellows, oranges, and red. Nili Fossae, this enhanced color portion of the floor of Nili Fossae contains a wonderful mixture of rock types known as melange. Nili Fossae is a graben or down-dropped valley. Much of the melange is a ejectiform, a larger crater to the southeast. Impact cratering is a great way to mix up rock types. Many of the materials have been altered by water. The parallel scarp-crested ridges are wind-blown sediments. And on the right-hand side, the frost-covered dunes in a crater. Dunes are often found on crater floors. In the winter, at high northern latitudes, the terrain is covered by carbon dioxide ice, also dry ice. And in the spring, as a seasonal ice sublimes, many unusual features unique to Mars are visible. On the floor of this crater, where there are no dunes, the ice forms an uninterrupted layer. On the dunes, however, dark streaks form surface material from below the ice is mobilized and deposited on top of the ice. In some cases, this mobile material probably slides down the steep face of the dune, while in other cases, it may be literally blown out in the process of gas release. similar to removing a cork from a champagne bottle. View of the angel with a big heart at the south pole of Mars. The DLR, a high-resolution stereo camera, HRSC, has been mapping the red planet in unprecedented resolution in 3 dimensions and in color. Since 2004, as part of ESA's Mars Express mission. And in images recorded on November 8, 2020 during orbit, a yet unknown nearly 100-kilometer long angel figure near the south pole of Mars appears to want to greet Earth from a current distance of approximately 100 million kilometers. And on the right-hand side, NASA captured blue ripples on the red planet. NASA says that blue ripples reveal the secret of how the wind blows on Mars. On the following pages, you can see, or will show you preliminary work for a joint project with Michael Plichter. These are attempts to familiarize myself with the material. I put Stevaform Gießmasse from Glorex into molds and tried to create some structures. After that, I painted them over with Modern Options Primer to create a barrier layer so I could continue working on them. I used different primers or foundations, iron primer and copper primer. And for the iron primer, there's a simple oxidizing agent that acts as a catalyst for the oxidation process. And there are various oxidizing agents for the copper primer so that different effects can be achieved. These are again the untreated areas. And in comparison, the first layer with the oxidants. Here they applied the funds freshly, and you can clearly see that the colors are still wet, and some structures are now easier to see, others less so. And this is a finished facade. In comparison, you can clearly see that the surface has once again changed significantly. In nature, of course, such processes take place much more slowly. The musician Rick Wakeman found a different approach to Mars. He's a passionate astrofan himself and is intensively involved with the subject of Mars, as can be seen in this interview with the magazine Raumfahrt Konkret. But he also deals artistically with Mars. Many of his compositions and albums are dedicated to the red planet. And who knows, maybe one day his music will be played on Mars. Back to Earth and Mars. Left is a view of Mars. It's a screenshot of a 3D image, and on the right hand side you see an image of the Atacama Desert. The surface structures are similar, only the sky is different. I was traveling in different deserts of the world, and I noticed one thing. The settlements in the deserts or oases are all surrounded by walls. I observed it in all deserts of the world, and this is not only for protection from wild animals, but also as protection against winds and storms. Here you see an overview image of a resort in the desert. As you can see the wall. And then I looked at the different designs for the Mars habitats. Here's a random screenshot from Google search, and the bases are either underground or on the surface, but never surrounded by walls. Even if they are underground, the entrances are on the surface and the sun could blow them over. We all know there are sunstorms on Mars. I picked out an example. This is a 2019 winning design of a NASA competition. And if you surround the space with a wall, And I've seen the science for stone or brick productions made of from regolith. So it would be possible. Also it would be possible to do this wall, as they would look different, of course. Then you would have a huge canvas for artwork. Life on Mars will be very hard, and it will be many decades before, if ever, the first human being is born there. But it would make the life of people on Mars much more colorful because there is no nature. But we want more. We want to bring art to Mars. In July this year, our first Space Renaissance Art and Science Festival took place at the Aschenhold Observatory in Berlin. And we had a really nice program about space art and space science. These were our sponsors and collaborators, and Space Renaissance International, together with the Mars Society and the Planetarium Berlin Foundation, launched the art project Art Goes to Mars. Art Goes to Mars is an international collaborative artwork and gallery of ideas worth sending to Mars. Art Goes to Mars aims to be the first culture event on Mars and will send 100 artworks to the Mars as early as 2030. And we are developing a culture for future interplanetary society. With Art Goes to Mars, we would like to lay the first cornerstone for a library on Mars. And it is a symbolic gesture that has a real influence, a way to reboot culture, rethink our values, and for better living on Earth's planet. We hope to bring the best of humanity to the Mars and to bring the benefits of the Mars to all people on Earth through a sustainable exploration process. Our initiatives connect art, Moon, Mars, and beyond. This includes the organization of meetings, workshops, art science-based classes and projects at various universities, sessions at international conferences, art exhibitions, musical and visual performances. So I hope the movie is running now. There should be a movie now. Oh. Hello, welcome to the rooftop of the Aschenhold Observatory in Berlin. You can see in the background the longest lens telescope on Earth with 21 meters. The Aschenhold Observatory was founded in the year 1996 and by the founder Friedrich Simon Aschenhold. And here in this historical place, our Space Renaissance Art and Science Festival takes place. And I'm so excited to announce our new project. Together with the Mars Society, Space Renaissance International, and the Planetarium Berlin Foundation, we want to launch our new project, Art Goes to Mars. Why art goes to Mars or to space? Art belongs to humanity, and that's why art has to go with us if it comes to space.
Why is art an important part of our effort to explore Mars? And the reason is it's because artists can see with their minds what other people have yet to see with their eyes. And so they can bring Mars to us, and not only the Mars of today, the Mars that could be photographed, send cameras to the right place, but could see what is going to be there. To basically make the vision sensuous, to convey to people what is actually there in a way better than a camera can, but more importantly, to portray what could be there, which no camera can.
What does it take to bring our civilization beyond the cradle of the Earth? it will take some scientists, some engineers, some astronauts, some architects, and all the disciplines. And we want to inclusively engage all humanity. But of course, as humanity, we have to bring as well all areas of art. And for this reason, Space Renaissance International, together with the Mars Society, are launching a new initiative to bring art to Mars. And this year, we are organizing a number of events, the Space Renaissance Festival in Berlin, but as well event at the International Astronomical Congress in Paris in September, where we will all gather and we will have also various proposals of art that we can send to Mars. So join us and let's all go beyond our cradle to the Earth, to the Moon, and to Mars. Thank you.
We would like to ask you to send us your work of art. These can be fine art pictures, collage artworks, photographs, stories, science fiction, music composition, dances, theater presentations, or movies. Since the transportation is very expensive, we would like to collect the works on a USB stick and send it to Mars. At the same time, we will organize exhibitions and performances. We will select 100 artworks to start their journey to Mars. These work of arts will later be collected in a book. Maybe we can raise enough money to fund the shipping of this book as well. Then, with this book, in addition to our artwork, we would lay the first cornerstone for a library on Mars. And who knows, maybe your artwork will be included. Are you in?
Thank you, Sabina.
No, it's not really.
The video was a little choppy, but we got most of it. So thank you.
Okay, I have one sentence more. In conclusion, we can say that nature is a great architect and artist. Through science and technology, we can make it visible in a number of ways. And art can touch our hearts. It speaks to us emotionally. And if we think back to the times of quarantine caused by Corona, we will remember that we survived the loneliness well, especially with the help of art. What would our life be without books, films, pictures, photos, theater, and games? Art is part of our culture, part of our history, part of humanity. And that's why there has to be art on Mars if we want to live there. I thank you for your attention and I'm open for questions. The movie could not be seen.
Say again, please, Sabina.
The movie could not be seen.
No, we saw the movie. It was just a little choppy. The sound also was a little choppy, but we caught most of it. When we do this archive on YouTube, maybe you can email me the video and I'll make sure the version up there is much better. So,
okay.
Any questions for Sabina? Okay. Well, thank you so much, Sabina. We really appreciate your presentation and thank you. We'll see you soon.
Thank you.
Thank you. Start with the video.
Yeah, we'll start with the video.
Okay, our next speaker is Kai Statz. So I don't know if you guys are familiar with Biosphere 2. It's a little facility about 2 hours south of here, roughly. And I had the opportunity to get a tour there along with a lot of our volunteers on Wednesday, so the day before the conference. And Kai led us around as well as the director of Biosphere 2 Hall. And we really had an amazing time. And we're really thankful for him that he put that together. So Kai is going to talk about the SAM, which is the new Mars analog at Biosphere 2 that he's been developing.
Excellent. Thank you. Can everyone hear me okay? Volume's good? Okay, excellent. Thank you. Thank you, James. It's a pleasure to be here. It's wonderful to be back in person again, and thank you for coming early on a Sunday morning. We're going to start with a video to wake everyone up. It's a 3-minute video that summarizes the first 18 months of construction of SAM, which is our hermetically sealed, which means pressurized habitat that we've been constructing at the Biosphere 2, and then I'll move into the more formal presentation. So enjoy. Let's see if this works.
You know what? Let me redo it because I want to make sure the Zoom audience has the sound on the video, because I don't think I checked that box.
We're now at about 600 parts per million.
Take our zeolite, which is our adsorbent, and add it into the scrubber system, into the sorbent bed.
Okay, let me get this in. Oh, that's the wrong one. Let's see, we need to switch to my presentation. Okay, thanks. So I want to, just before we dive into the details, I want to share everything you saw in that presentation, in that video, was done over the course of 18 months with volunteers from about 4 different countries. We had 20 volunteers during the heat of COVID. We did very well in terms of the ways in which we managed that. And we did all of that for $168,000. And so we're very pleased with with what we've accomplished. The contributions, the financial contributions came from the University of Arizona and from a private donor, and those are continuing to roll in, which is fantastic. We now have enough funds to complete our effort through the rest of this year, which, as I will share in the presentation, will bring us to a fully functional, hermetically sealed analog by the close of 2022. Thank you.
And I apologize, the director of Biosphere 2 is John Adams, not Paul.
It's okay. It's the last day of the conference, it's okay. So again, this is Sam, a space analog for the Moon and Mars at Biosphere 2. I'm going to give you just a brief history of analogs and the role that they have played throughout the history of human space exploration. And then we'll work into what we're doing specifically. So the question that we fundamentally ask ourselves repeatedly is, what does it take for a species to become interplanetary? That's the question all of us are asking here today and throughout this conference. It's what Robert's been asking for many, many years, and we've been working to solve that question incrementally over the course of decades. This is a wonderful artist rendering by Brian Vierstig, and it gives us a sense of what we're shooting for. Maybe not the 1 million-person city yet, but maybe not the first tin can that we land on Mars, but something in the middle, a 3rd or 4th generation habitat. But to get there, there's a lot of work, there's a lot of unknowns that we have to solve. And we use analogs here on Earth in order to solve many of those questions and to fill some of the knowledge gaps. So just a brief history. Most of you are probably aware of all the analogs, but I'll go through it anyway. So we've started in the upper left-hand corner with the work of Gene Shoemaker and the Apollo astronauts at Meteor Crater. That was an outdoor or an external analog. We have the underwater, the Neutral Buoyancy Lab at NASA. We have Hera and BIOS 3 and the work down at the Concordia Station, High Seas, NEMO, Lunaris, and of course our favorite, the MDRS, the most famous and certainly the most well-known of all the Mars analogs today. And here's just a brief list of the ones that, and there's probably more that I'm not aware of, but these are the brief list of the ones that are active or recently been active. Those in italics are the ones that are pressurized and or sealed. And then we come to Biosphere 2. So Biosphere 2 is a very unique facility. It was the largest, certainly the most audacious attempt at or I should say effort in a sealed analog. And if you look at some of the early renderings, the early artist renderings and the work that the Biospherians did, it was much more geared towards how will we live on Mars. And over the course of their work as a team, over the course of that decade together, they really evolved the effort to becoming more about how do we as humans interact with the world around us? What is the relationship between the humans and the ecosystem in which we live? And of course, they divided that ecosystem into specific biomes, some of which were directly responsible for their ability to eat and to process the air, and other ones which were really test beds for the variety of plants that we might be able to bring someday to another planetary body. I do want to make a statement that is very, very important. Too much of the media, even today, 30 years later, uses the word failure with Biosphere 2. The word failure and experiments do not go in the same sentence or even the same paragraph. If you're conducting an experiment and you learn something, you didn't fail. Yes, they ran out of oxygen. That's part of the experiment. We'd rather run out of oxygen here on Earth and understand why than on Mars, where we don't have the ability to recover. So there were some challenges. We learned from that, and it was an incredibly successful project. In another talk with more time, I would go into the details of what was accomplished throughout that. I can also answer questions after this, of course. So this is the agricultural space in which they grew all of their fruits and vegetables for their food. This is the ocean this is an older photograph, probably a couple of years ago. We've actually removed a lot of the algae since then, using both mechanical and biological means by introducing certain crabs. So there's a full ocean. It is the world, as far as I understand, the world's largest enclosed saltwater research ocean. We have a full rainforest. Most of the plants here are the original plants from 30 years ago. They were 2 or 3 meters tall when they were introduced. They're now 90 feet tall, which is phenomenal, over 25, 26 meters tall. Now, this photograph is wonderful. This is 1987. This is the test module. This is the prototype, the second prototype. The first prototype became the gift shop. The second prototype, called the test module, was used to test the function of the sealed windows and the sealed system with a stainless steel welded floor. And this was about 200 or 300 meters away from the Biosphere 2 proper. So while Biosphere 2 was being built, this facility was being tested. And the biospherians took turns living inside, one person at a time, all of their air, food, water, and human waste fully recycled within a 400 square foot building, about 11,000 cubic feet total, including the lung. So this is the building that we started with. We had the opportunity to take this 35-year-old building and refurbish the building. So that's what we did from January 2021 through June, as you saw in the video. And so we had the opportunity to start with a very complex and otherwise very expensive building and spend that 6 months refurbishing it to getting it back into a fully pressurized state. Remarkably, it was in pretty good condition. For those of you who have lived in the desert, you know that the desert likes to move into buildings very quickly. So having been abandoned for about 20 years, we had to send an eviction notice to a number of creatures. And we had to dig out a lot. We had to use a jackhammer and dig out a lot of soil that was in there. This is the same facility today. And I won't have time to go into all the details of everything we've done. However, on our website, which is samb2.space, we have photo essays for every single step, usually 2 to 3 essays per week. There are thousands of photographs, over 110 essays. Everything we're doing is recorded. The science of it, the reason why we're doing it, the stories of the folks, the volunteers and our staff that are working on this. So we have a complete log, a really solid story of how and why we've accomplished this. So I just want to give some artist renderings because I haven't had yet a chance to fly a drone overhead or take a shot from an airplane. So this is the best way to give you the overview. On the bottom left-hand side, we have the original test module, and then we've added on a 20-foot in the center, a 20-foot shipping container, which is the workshop that will have a 3D printer, a sewing machine, a soldering bench, repair facilities, so you can both repair and create things while you're in sim. And then we're looking at the end on the right-hand side of the 40-foot shipping container and the airlock. The airlock is a fully functional airlock. It will act as a pass-through airlock, meaning we'll pass air through so for a certain period of time, because obviously we're not moving out into a vacuum. So it can't function as a proper airlock simply because we can't evacuate the air around it. And to the adjacent side of that, we have the what was the greenhouse for the rainforest. So if you had visited the biosphere in the early 90s, while the biospherians were inside, there was a botanical garden outside of the biosphere proper, in which you could go as a tourist and go through and see all the plants, all the animals and the functions that are inside, but on the outside. So we've completely refurbished this 6,400 square foot greenhouse, and that will become our indoor Mars yard. And just yesterday, I had the pleasure of meeting with Dr. Jim Bell, and he's helping guide our effort as to how to design that space to make certain it's as geologically correct as is possible given what we have here on Earth. So just a basic timeline, is not going to read this to you, but where we are now, we're in phase 3. And just last week was our first week back. We always take the summers off. We have from now until the end of December and a little bit into January to complete the functions, to complete this construction process and bring it to a level of functionality for our first visiting teams. We have 7 teams signed up for 2023 already. So the principal components, again, not going to read all this to you, but the key efforts, most important thing is the movie theater. We've got to have a really good movie theater inside. We have a greenhouse, which is the controlled environment, the crew quarters, a kitchen, fully functional kitchen. We believe that food, as at MDRS, the kitchen is the center of really the team experience. It's where we spend a lot of time together. It's how we cook together, which is very important. It's how we share our cultural differences through our food. We want to make certain that we have that quality of environment as well. We have a workshop, as I mentioned, because we are pressurized. Now we're pressurized at approximately 1/10 of a PSI over ambient. Doesn't sound like much, but that's all we need to make certain that we are biologically sealed and we're not seeing contaminants coming in during the missions. But to give you a sense of that, every 25, we have a number of windows. There's 16 windows, which are 25 square feet each. There's 360 pounds of pressure on each one of those windows. So even at 1/10 PSI, it's still a phenomenal pressure. It still is enough to pop your ears if you open the door quickly. We have an indoor Mars yard, an outdoor Mars yard, and we use fully pressurized spacesuits, as you saw in the video. That was a prototype, an older model from 3 or 4 years ago that we were using just for that video. And we now have 2 brand new spacesuits that were built by Smith Aerospace Garments out of Portland. And they've been tested at 70,000 feet underwater, cold chambers, vacuum chambers. It's the real thing. They're highly functional and very, very high quality suits. And as we'll be talking about a little bit later, we are integrating a full sensor array into a live data feed in HAB that will also be working to do model validation for later use within our model itself within CMOC, which Ezio will be talking about next. So what does one do at SAM? What do people do at Analogs? Perhaps this is the one conference that knows this better than any other, but I'll share with you a little bit of some of our science objectives. So we have 5 science objectives that are core to our team. It doesn't mean that if you come to SAM, you have to do these things. These are just things that we're excited about. You're of course welcome to bring what you would like to bring in or build on these. So we, as far as we know, we will be the first analog to transition from physiochemical, meaning machine-based, to bioregeneration or plant-based life support systems. So some of the crews will come in and there will be nothing growing in the hydroponics or our small soil beds. We have a fully functional zeolite-based CO2 scrubber today that we received from Paragon Space Development Corporation. We're in the process of building a larger scale swing bed. We built a swing bed CO2 scrubber from the ground up last year with a 5-person engineering capstone team from the University of Arizona, fully functional. Most of the parts came from Ace Hardware with a little bit of machining at the University of Arizona. It's not rocket science, but I guess it could be rocket science, depends how far you want to take it. And so we will be building and operating a fully functional CO2 scrubber in which we can capture the CO2 and then pipe it into the greenhouse to release it to the plants again. Really, we're learning one of our fundamental foci is how do we close the air, food, and water cycles? And a study of the microbiome, we're working with the University of Arizona. They have a fabulous microbiological study program, and we're working with some of the experts there on doing sampling of that microbiological environment and understanding how does it transition, how does it transition and evolve over time with the movement of teams in and out of a built environment. We'll be testing pressurized suits, tools, and procedures, as I shared. And again, advanced computer simulation with real-world model validation, which is the cornerstone of any scientific endeavor. Build your model, test it, gain new data, revise your model, test it, gain new data, et cetera. So CMOC is very much a cornerstone to this. So CMOC, as Ezio will talk about in the next call, is a agent-based model with both a web interface, educational web interface, and a research backend built on 40 years of NASA data. And this was started right here at Arizona State University in 2017 with funding from the Interplanetary Initiative. And that was a project that I had developed, and it's now funded by National Geographic and by Biosphere 2. And we have some really exciting things, as you will tell us more about, including a live data feed and live interface inside of the habitat so that you as a team member will have a visualization of your quality of your air and quality of your water. Team research at SAM, as with all the analogs, there's such a variety. There's so many creative things. You look at what's happened to MDRS over the last 20 years, and there's so many incredible opportunities for teams to come in and really explore the variety and the depth and breadth of all the sciences, soils and hydroponics and aquaponics systems, food production, CO2 sequestration, converting regolith to soil, human factors, tools, and haptics, et cetera, et cetera. So really wonderful. So we're looking forward to all the creativity and what will be brought in. Who can apply? University professors and their students, industrial professionals, analog astronauts with a clear science foundation, astronauts in training. My associate Trent Tresh and I have co-founded a center of excellence at the University of Arizona called the Center for Human Space Exploration. And Trent led the first emergency egress training class in the University of Arizona swimming pool. He strapped a parachute onto a volunteer, shoved him into the pool, and he had to be able to disconnect himself from the parachute harness, swim through the water, and climb into an actual life raft, which is similar to what the Navy uses for emergency egress from ships. So we're going to be doing a full astronaut training program at the University of Arizona, and this is just the beginning. And also we welcome artists, writers, filmmakers embedded in the teams. University of Arizona Professor Christopher Kokinos has put together the first all-professor team from the University of Arizona. They're artists, writers, and filmmakers, and they'll be coming the second week of March to SAM. So we're really excited to see what they come up with. So we're taking team applications now. And before I go into this part, I also want to make it very clear that we don't see ourselves as competition to MDRS. Shannon Rupert, the director of MDRS, was really gracious in her support of us. She even sent her niece, and Attila, who's in the, her niece is in the upper right-hand corner, Attila is in the upper center, from MDRS to help us last in getting some of our foundation work done. So we really appreciate that. We see ourselves as complementary and different from MDRS. There's room for everybody. So we please come and come to our facility, go to MDRS, go to Plenaries. They're all unique facilities that offer something different for the analog astronauts. We have had volunteers from all over the world, over 20, 25 volunteers to date, some of which have become my full-time staff members. So just sharing some of those folks. On the upper right-hand corner is John Adams, who's the Deputy Director of Biosphere, probably the best person I've ever worked for. Absolutely just creative and a good listener, and pretty much says yes all the time. As long as as he says to me every day, just don't kill yourself. You can just do what you need to do and get it done. And so this is our current, some of our current staff members, and we're happy to be working with Anastasia, and Anastasia will be helping us throughout the next year as well. And I just want to close with a really unique story. I would encourage any of you who have daughters or granddaughters or girlfriends or wives, give them power tools for Christmas. It's a surprising, give power tools to everybody, but specifically to women. So this is Luna. Luna's 20 years old. She just graduated from high school about a year and a half ago. She's taking a gap year. She had not worked with power tools before. And she is now a rock star. She is fantastic. And she is just prolific with all of her skills and her capacity and her knowledge. And she is really instrumental in helping physically build this structure. And so I encourage all of my team members, if they don't know how to learn how to sketch, to use a notepad and paper, not because computers aren't necessary, but because they're not needed for rapid ideation, for getting those ideas out of your head and sharing with your colleagues. This is the fastest way. These are my sketches. Each one of these is about 5 minutes, 3 to 5 minutes. This is how we're designing and building our facility. We then translate these into the bare minimum necessary computer drawings to hand off to a welding team at the University of Arizona, or to contractors who are coming and doing some of the work that we can't do, which is minimal. So I really encourage all of you to really, whenever possible, get people out of the digital world. The digital world is exciting, but it's not the real world. Get them into the real world, get them working with their hands. It gives people confidence. They stand different, they see the world different, they can fix their own car, they don't have to rely on mechanics. There's a lot of exciting things that come out of that. So. And actually, this is what Luna then designed. So on her own, I said, we need sleeping pods. They need to be insulated. They need to be soundproof. Go. And so she did the research. She looked at some of the NASA functions, some of the things they've done, did her own measurements, did her own ergonomic studies, and she led the project and she built the prototype. She and my other employee, John Z, built this is about 3/4 of the way through the construction process. She did her own sketches in a notebook, went and bought all the materials at Home Depot, and spent about 2 weeks putting together the first prototype, and it's awesome. It's really, really cool. So we'll have 4 of these pods stacked inside of the crew quarters. They're modular, we can move them around, and when you're inside that space, that's your personal space. So in closing, I've said this many times now over the course of the last 2 years of working on this project. Living on Mars tomorrow is how we should be living on Earth today. And what I mean by that is that we are aware of and appreciative of every breath of air we take, every drop of water, fresh water, which is becoming increasingly scarce on this planet, every drop of water, every bit of food. It means that we're not eating beef 3 times a day. We're probably going to be vegetarian, right? Not for animal cruelty issues, not for those issues, but because of the incredible amount of resources that we waste on this planet on producing meat, when the same amount of resources could feed 8 to 10 times as many people. When we go to Mars, we're going to be living the way we should be living today, aware of our water, taking short showers. It's even the things as MDRS has emphasized. They have a finite amount of water. That's all the water you get for the whole mission, right? You have to be aware of how many showers you take and how many times you flush the toilet, et cetera. So I'd like to close with this, that our mission is to engage research teams from around the world in hands-on scientific discovery and to inspire the next generation to be engaged custodians of this planet while exploring new worlds. So thank you. I'll take any questions.
Philosophically, if we must give up meat so that the population of Earth can rise by a factor of 10, is that a appropriately meritorious trade-off?
I'm not, that's a good question.
So if you want 1/10 the lifestyle for 10 times the population, that's what you're saying is a good thing. That was your.
I'm not certain that there's a direct correlation there. I don't think that we need to increase the population of the planet by 10 times. And that by reducing the amount of resources does not automatically equate to additional people. It may happen that way, but it would be sad if it does. So I think the thing we need to look at, and I'll just throw two facts out. If you look at all the tillable land on planet Earth, all the land that we till for planting plants, 80% of it goes to growing grain for cows. 97% of all of the animal biomass on planet Earth is humans and their cows. All the zebra, elephants, wolves, rhinoceros, elk, deer, fox, coyote, rabbits combined is less than 3%. If I were an alien flying past this planet and took a look at what we're doing, I'd just keep flying. I'd wait a couple hundred years and say, these guys will be gone. I'll come back when it's empty. It doesn't make sense. It just doesn't make sense. And this isn't me saying you should all be vegetarians. It means that we need to all be aware of our impact by continuing to support a lifestyle, exactly as you said. It's not a necessity, it's a lifestyle choice. And the sad thing is that we as Americans have set the standard, meat 3 times a day. The rest of the world wants to be like us, and they're copying it as quickly as they can. So I know it's not what you came here to hear, but as long as we're on the subject matter, so. Yes, sir.
Yes, awesome. Yeah, once a week is fine if you want to get started on it, you know. You mentioned 3D printing and soldering, two processes which I would normally go open the window. What do you do to anticipate and handle outgassing, toxic metals, things like that?
So then I will just take an usual mic.
I'll fix this up. We have two things.
Okay, can you hear me? We're back. Okay, excellent. Yes, thank you. You're absolutely correct. In those, whoa, was that me? That was not me. Okay. In that situation, yes, there will be off-gassing of fumes and such, 3D printers. And so we are putting in activated carbon filter hoods and trying to encapsulate that environment in which those facilities will be operated so that we can clean the air. That's correct. And we will have active, obviously carbon dioxide, but also VOC sensors. We have a sensor array that we've been working with for the last 6 months, and we'll be testing that further for the next 2 months. In fact, Ezio's here from Italy to work on those systems. So I don't have the final answer, but those are certainly things we're aware of. And the good news is we have Paragon Space Development Corporation in our backyard, and we've worked very closely with them for the last 3.5 years. And so when we can't answer something, we drive down the street and they can answer it for us. It's why we have experts on our team. Thank you.
I got a brief intro and a quick question. It was at the very second Mars Society conference that I met some of the original biospherians and learned that the popular media portrayal of it as a failure was false. And I've wanted to visit it ever since. And it so happens it's a brief detour on my way home. So my question is it open today?
Yes, Biosphere 2 is open 7 days a week, 364 days a year, if I remember right. They open at 9 a.m. They close it. The last tour on Sunday, it starts at 3 p.m. and stops at 4. And it's a fabulous tour. There's so much going on there now today. There's agrivoltaics and photovoltaic studies, and we have a shipping container that's producing 800 heads of lettuce every 17 days in a hydroponic system. And there's a lot of wildlife. There's javelina and deer and fox and bobcats and mountain lions, and it's an exciting place. So I really encourage you to go. I think you'll enjoy it.
One of the more publicized issues in Biosphere 2 was the inability to generate enough oxygen long-term for subsistence and the fact that oxygen had to be added to the habitat. Is it going to be a focus at some point of SAM2 to revisit that and see if a self-contained system can be designed that will produce enough oxygen for the long term? And if so, what have we learned from Biosphere 2? What would we do differently the next time around to fix that?
Very good question. Thank you. Well stated. I will correct one thing. It's not technically that they couldn't produce enough oxygen. The oxygen was being produced. It's that the oxygen was being taken up by 2 very heavy reactions. So in fact, I just met the original soil scientist for Biosphere 2 4 days ago, Robert. He visited, and the explanation is that the oxygen was being consumed by the heavy microbial activity in the soil. They handcrafted their soils to make them as rich as possible, particularly for the rainforest region and for the agriculture region. They actually went to a nearby sewage wastewater treatment plant and took that material and mixed it into their soil to make it as rich as possible so the plants would grow. Makes sense, right? But those same microbial functions, just like us, oxygen in, carbon dioxide out. In addition, it was a double whammy. The concrete was curing, and the process of curing concrete, and we're talking about, I don't remember how many cubic feet of concrete. It's a lot of concrete. And that concrete was still wet for years afterwards. Those two functions reduce the atmospheric oxygen drastically. So today, if you were to seal up biosphere, you wouldn't have those issues, and you would be much more readily capable of producing and maintaining that sustainable atmosphere. Now, in the second mission, the first mission was 2 years. The second mission was 1 year. They adjusted things. They took one person out, so it was only 7 people instead of 8, and they had synthetic lights over the grow space. And they changed the number of foods from something like 20 food cultivars down to the necessary 12. So there's already lessons learned from the first mission to the second mission, and the second mission was able to sustain that quality of atmosphere just a few months after, I think it was 6 months after the first mission ended. So already lessons learned. But the primary lesson would be, don't make your soil too rich, and we're probably gonna use hydroponics anyway on Mars, at least initially, and don't move into a habitat that has wet concrete. How are we doing time?
Hi.
We're good? We're done? Okay, thank you, everyone. Appreciate it.
Running out of time.
Okay, our next speaker is Ezio Melotti. And he's the lead developer on the CIMOC Mars Habitat Simulator, and he's gonna talk about increasing fidelity of the CIMOC Mars Habitat Simulator. So welcome.
Okay, hello everyone. Can you hear me? So I'm Ezio Melotti. I'm the lead developer of CIMOC, and I'm also a core developer of the Python programming language. If any of you here is a developer, you probably know Python. And I've been working with Kai on this project for 3 years now. So what is CIMOC? CIMOC is a scalable interactive model of an off-world community. What does it mean? We want to simulate what happens in a closed off-world community so that all the agents and currency that we have inside can interact. We want to see how they interact, and over a span of months, weeks, or longer. So we create this simulation to see how it works and simulate things like STEM or other like based on Mars. A bit of history of this. So it was the initial concept was from Kai Stats, who did the talk just before mine, and it was the idea came out in 2014. After a few years, he managed to get some funding from the Arizona State University, and with a capstone team, he started working on CIMOC. So the first capstone team created the foundation of what CIMOC is today. In 2019, I joined the project, and it was like a bit of a bad moment because there was no funding that year. But luckily, just the next year, the National Geographic Society funded CMOC, and we start taking out from there. And nowadays, we are still funded by the National Geographic Society, which are also hosting CMOC on their website to make it available to everyone for free. So big thanks to National Geographic Society. And the team is growing. So in 2021, so last year, we got grant on our team. We got another capstone team working with us. And we are now receiving additional funding so that we can keep growing and expanding. And it's a very exciting time. There are a lot of things going on, a lot of cool things, and I'm super excited of being part of this project. So a bit about the design of CMOC. So CMOC has two main parts, what we call the front end and the back end. So the front end is what you see when you go on the National Geographic website. It's a web interface. It allows you to create a mission, so set up a mission where you decide how many people are going, how long are they going to stay there, how much food do they bring, how many plants, what kind of plants. And you can set all these parameters to design a mission, and then you can run the mission and you can see what happens. So are the humans going to survive? Are the plants going to die? What is going to happen? And you can use CMOC to do exactly this. And this is the web interface. So this is where you create a mission. So you can see you can select the number of plants, the number of solar panels, the batteries, and so on. We also have like a 3D rendering that changes in real time to show you how it might look like. It can have like, depending on how many solar panels you have different sizes of greenhouse habitats, depending on the human. Like if you get like a small greenhouse, you might not have enough space for all the plants to sustain the humans. So you can change all these parameters to set up an optimal mission. And then we have the backend. So the backend is an agent-based model. I will tell you a bit more about this just in a few slides. And it's scalable, so it's hosted on the cloud so that it can support a lot of people. This is very challenging for us because we are receiving like students and people and researchers. Everyone loves it, so we get a lot of traffic, and scaling up to support everyone is quite a challenge. And also because to calculate all this simulation is very computational intensive. So it's like a big challenge, but it is like a challenge that I like to face. And we also have different type of backends. So we started with the simulation backend, which is what I was talking about. So you can specify how many humans you want, how many days, and how many solar panels, and so on, and run a simulation to see what's going to happen. But recently we added a different backend. So this is what we call the live backend. The live backend uses the same front end that we use for the simulation, but instead of showing the data that we have simulated, it shows real-time data. So I can show you how it looks like. This is the main, what we call the dashboard. So in the dashboard, you can get this, you have different panels. You can configure them however you want. You can add more panels, you can remove them, you can move them around, and you can visualize different kind of information. So we have tables, we have graphs, we have different kind of information, and this allows you to see what's going on in the mission. If you look at the bottom, you will see there's like this scrubber, that green line there, and there is like a play button, and on the bottom right, there are like the number of steps. So the steps is the unit that by default is like 1 hour. So you can see hour by hour what's going to happen in your habitat, depending on the duration of the simulation. So for example, here, if we have like a 1 month long simulation, hour by hour, for example, on the top in the middle, we have the production and consumption of energy. So you can see the solar panels produce energy during the day and they don't during the night. You can see how the atmosphere changes. You can see how the humans are doing, the levels of the oxygen, CO2, and other elements. You can see on the top right, there is like a table that shows all the storages, like how much water you have, how much oxygen you have, and how much food you have, and so on. And you can scroll back and forth and see at any point in time what's going on. And this is the simulation mode, but the live mode looks exactly the same, but the data keeps arriving and keeps updating. So I mentioned before the agent-based model. So what we did to simulate this, we use this so-called agent-based model. What does it mean? We have an agent for everything. So we have humans are agents, plants are agents, e-class modules are agents, solar panels are agents. And what do this agent do? So they have inputs, they have outputs, they have storages. So for example, a human, when it breathes in oxygen, the oxygen is temporarily stored inside the human. And then at some point, the oxygen will come out probably as CO2. So it will bind with the carbon and come out as CO2. And we also have characteristics. So we have things like the deprivation. A human cannot go more than 21 days without eating, or like 3 days without drinking. So all this agent has these characteristics so that we know how they behave. And the agents also exchange what we call currencies. So we have oxygen, we have CO2, we have kilowatt hours, we have water, and they keep exchanging in a loop. And so this is an example. So this is a human. So you can see the human get like certain inputs. So it gets like water, it gets like oxygen, food. These are all things that are necessary for the human to survive, but it also produces a lot of output. You know, humans are pretty gross. They have like carbon dioxide, they sweat, they expel urine, feces, heat. All these things are tracked by our system. So what happens when you have, so if you have like only one agent, it's kind of easy to track what's going on. But what happens when you put several humans in a closed habitat? What happens when you add plants? What happens when you add other things? You get something that looks like this. So this is a slide from the Lunar Palace system flow. So this is a closed loop, closed system. And you can see how you have like plants, you have humans, you have atmosphere, you have water storages, solid waste treatment, reclaimed water. So all these parts, so all the squares or circle that you see here, these are what we have, what we call agents. And all the arrows that move around is what we call currencies. So these currencies go from one agent to the other. They transform, like I say, for example, the oxygen become carbon dioxide and then gets broken down into something else. It goes into the plant, which becomes actual carbon that makes the plant grow. And it flows through the system in a closed loop. And this is another example. So this is from Sean Gellenbeck, is a PhD student that is working with us and using CMOC for his studies. I will tell a bit more about that. But this is an example of another closed loop. So this is a kind of a recurring theme. Like every time you have a closed environment, you have this agent that interact with each other and exchange currency. And we want to know how this is going to work. That's why we created this software to simulate it. And to make it flexible, we designed CMOC so that we can basically model everything. So you can also, if you wanted to, you can have every kind of agent, even, I don't know, the stock market. You could use the CMOC, you create agents that matches something from the stock market, and you can use CMOC to predict what's going on. So we design it in a way that is very flexible and very easy to expand. And so you might be wondering, how do we know like how much a human needs, like how much food, how much water? What about the plants? What about the e-class system? What about all these agents that we are adding to the system? So we use data from different sources. One of the major sources, it was the NASA baseline values and assumption, so the BVAD document. We also work with Ray Wheeler. I guess many of you probably know about him. His plant studies provided like a lot of data, which is very valuable for us. And not only we are using existing study, we are also producing original research. So members of our team are doing plant studies, for example, to see how the plants behave in different conditions. So Grant was working with last year on like trying to figure out what happens when there is a low CO2 amount, what happens to the plant, because the problem is most of these studies are in optimal condition, but in our simulation, we want to know what happens if there is not enough CO2 or not enough oxygen or something else is missing, or like can the plant survive 3 days without any light? What happens if we provide light after 3 days? So there are a lot of difficult questions that we are trying to answer. And in addition, we also have, for example, for the E-class data, we have, so Paragon review our data, and we constantly research and add new agents and try to make it as close to reality as possible based on the available data. And to give you an example, I'm not going to read through all this, but this is the data from Ray Wheeler. So you can see there are like a lot of plants here, and for each plant, we have a lot of values. So we have a pretty accurate model of what's going on. So we have things, for example, when you harvest the plant, what's the mass, what is the edible mass, the inedible mass. We know how much water we need, how much CO2, how much light, and different plants behave quite differently. And this is quite interesting to understand where like some plants take a long time to grow, and maybe we have just little caloric value, whereas others take much less and they have higher caloric value. But it's not as simple because some plants require a lot of light. So depending on the plant that you want to have inside your habitat, you might need a lot more solar panels. So that might not be feasible depending on like the space you have on your rocket to bring up solar panels on Mars or somewhere else. And another challenge, as I said, like you know that because of the law of conservation of mass, the mass in a closed system is constant. So nothing is destroyed, nothing is created, everything is transformed. So we want to eventually, so this is something we've been discussing for a while, we want to be able to figure out where each atom is. Of course, not at individual atom level, but let's say if I breathe in oxygen and then I breathe it out, that becomes CO2, as I mentioned. So we know that there's a certain amount of oxygen that gets inside my body as an input and gets out combined to the carbon to make CO2. And we know that this CO2 goes into the E-class module, but maybe breaks it down, or it goes into a plant. And we know that the plant grows and the mass increases. So now some of the carbon is there. And we want to be able to track all this to ensure that the system is accurate and nothing is created, nothing is destroyed. So unless someone nukes our base and we have a nuclear reaction that produces like change like mass and energy, in theory, the amount of mass should be constant, and also the amount of each element. So the amount of carbon in the system, the amount of oxygen, they all to be constant. So we're working on always striving to improve the accuracy. And so this is a good overview of what CMOC is and how does it work, how it works. So who is using CMOC? We have two main target audiences. So we have researchers and educators. So it's like CMOC is both for research and for education. So for research, we have, for example, right now we have 2 PhD students using CMOC to do studies, for example, on algae and mycelia, and also on the E-class that is going to be inside SEM. And the way it works, you can create custom agents. So CMOC supports the creation of custom agent. For example, you can take a mushroom or an algae, and if you know the values, so the inputs and outputs, you can create a new agent. You can add it to the system. You can say this exchange oxygen, CO2, and water with these other agents. You create a connection, and then you can run the simulation and see what happens. And Sean is doing this with CMOC first, and then in real world to see if the data matches. And for researchers, CMOC is also available under an NDA. So I already mentioned that it's free for everyone to use on the National Geographic website. but we also make it available to run like a local installation that is like more customizable for everyone. And this is an experiment, the experiment that Sean is doing. So this is a closed container that contains algae and mushrooms, and which are like exchanging currencies in a closed loop. And when we have education, so not only is useful for researchers, but the kids love it. We have several teachers from grade 5 to grade 10 for all kinds of students, and the kids really love it. So they can play around. It has like a intuitive interface. It kind of looks like a video game in a way, but unlike a video game that usually video games are like fun to play, but maybe not very scientific, we have like hard science behind everything we do, but we present the data in such a way that the kid can understand it and can play with it and have fun and learn a lot in the process. So we have a lot of teachers using CMOC in the classrooms. We also have a science center and museum. So we recently developed a kiosk mode so that museum and science center can put a kiosk where people can go and use CMOC. And I want to share some of the photos that the teacher sent us. So these are some of the kids from Gretchen, and they were so excited about CMOC that they built a small cardboard habitat, and using the live mode of CMOC, so using the web interface, we send them some CO2 sensor, and we were using the web interface to see how the level of CO2 increases both in the classroom and inside this cardboard Mars habitat. So this is amazing. And here we have other students, and here you can see that on the left of the photos, there are like 2 students with CMOC having like 2 different panels open. So maybe they're on the same simulation, but with a different set of panels, they can monitor 2 different parts of the system. They can make hypotheses. They say, do you think this is going to work if we increase the number of humans, or should we put less? And they compare the result and then do another simulation. We do hypotheses, they test, when we see the result, then we go back and try again. And by doing this, we learn. And here more students like on a tablet playing with this. And so we got some feedback from the students. And one of the coolest things that I heard from them, many students said that it's not only about Mars. So we are not learning like how is it to live on Mars. They say that they are also learning how to live here on Earth, because by seeing these systems and thinking the relation between plants and humans, we need plants to survive because plants give us oxygen, and the humans give CO2 to the plants, and we need light, we need different things, we need water. So they realize that it's not just us humans taking all the resources for us and doing what we want while we destroy the planet. They realize that we're part of a system, a closed system, because the whole Earth is like a closed system, and we need to find a balance. We need to keep the water clean. We need to avoid the greenhouse effect. We have to, like I was saying, like don't eat too much meat. And this was very insightful. So these students learn to appreciate more what it means to live on Earth and be more careful with the environment, like the way they treat the environment around them. And I think this is like a great success story for CMOC. And okay, so currently CMOC has a couple of locations. So we have Mars, and we are also working right now as we speak. We are working adding the biosphere too. So we want to simulate biosphere too. So what happened before and what's happening now, and even like hypothetical scenarios. We want to model biosphere too. And we are currently working on this one. And in the future, we are planning to add more location. So the system is designed, so even if the focus initially was on Mars, the system is flexible enough that we can add more locations. And in the future, we're planning to add the moon, the orbital reef, and we have like with National Geographic, we are going to also add some Earth systems. So as I said, it's like an exciting time for CMOC and SEM, and we are expanding. We have a lot of cool plans. So keep an eye on what we are doing, because it's going to get even cooler. And so in the previous talk, Kai mentioned what we're doing with SAM. And one key thing that we are working on in the integration of SAM and CMOC. So the first thing we are going to do is using the web interface to monitor what's going on inside SAM. So we are working with, we already tested over the past few months with sensor of arrays. So we can get several, like an array of sensors. So we have like CO2 sensor, oxygen sensor, humidity, pressure. We can get all this data from different parts inside SAM, and we can use the web interface to see what happens. So that every crew member inside SAM or outside SAM in mission control can know at any point if all the levels are okay throughout SAM. So in the greenhouse, in the crew quarters, and so on. And another extremely important thing is the data acquisition and model validation. What does it mean? So far we were just like simulating, but we had actual data, but it's difficult to know if what we are simulating is correct. By repeating the same experiment inside SAM, we can get actual real world data that we can feed back into the system, so we can get better simulation. And with the better simulation, we can plan a better mission on SAM. We can verify what happens if it matches the simulation, feed the data back in, and this is a loop that improves both systems. So this is a very interesting thing that I'm looking forward to do. Like I just arrived here like a few days ago, and I'm going to stay here for the next 3 months working on this project. And finally, we're also talking about using machine learning to, there are like a lot of possible applications. So we're still in the early stages and discussing, but we could use like machine learning, for example, to find optimal configuration. So for example, you could say, I want this many humans and I have this much space on my rocket. What should I bring to make them survive this amount of time? And we can also do kind of monitoring and controlling the interaction of all the agents, because, you know, for example, the E-class, we want to start scrubbing CO2, not when the humans are dying because there's too much CO2. We want to be able to predict that, for example, we are going to harvest the plant next week. And when we harvest the plant, we are not going to sequestrate enough CO2. So there will be like a spike in CO2. So we need to maybe start scrubbing CO2 a bit earlier. So there are a lot of cool things that we can do, a lot of cool things that we are already doing right now. So you get the idea. It's very extremely cool, at least for me. So I think that's it about my talk. So thanks for listening. And if you have any question, I'm here to answer. Okay.
Is it closed source or open source? And if it is closed, do you know why? And are there any good alternatives someone could look at if they wanted to do some work themselves?
So that's a great question. I was actually waiting for it. So as I mentioned, I'm a Python core developer. So I've been for over 10 years. Most of the code I wrote is open source and is out there, is in most of your computers. My code is running there. So I love open source, and I want CMOC to be open source, but it's not yet open source. If you are a researcher, you can get the full source code. We can help you configure things. You can get access to it under an NDA. And eventually, I'm pushing Kai, and Kai is on board with me, to make it open source, because I want people to use it. I mean, we did a cool thing. I want to share it with everyone. So we want to make it eventually open source. We aren't there yet, so we are discussing how this is going to affect our business model. But yeah, I certainly want to make it open source. And probably we will make some components, some part of it open source, and we'll see. But at the moment, it is not open source. But we can provide the code if you are a researcher for yourself. But yeah, great question. Thank you for asking. Yeah.
So, very interesting. Is your system, SIMOC, capable of connecting the environmental data inside SAM to the particular health outcomes or maintenance of health in the crews?
Yeah, so once we get the data, we can in the front end, for example, we have kind of some thresholds so that we can start producing warnings if, for example, the CO2 rises above a certain limit, and we can have like different levels. So this is something we can do, and certainly we can expand. I mean, we are currently developing, so every time we need like something new, we just sit there and code it. But right now, the live data is mostly visualization with some kind of threshold that you can set to show warnings. So this is what we have right now, but we are going to expand it now.
Okay, looking forward to that.
Yep.
Hey, if you were asked by SpaceX to construct this on Mars within 4 years, how certain you are that the humans are going to survive, or is it feasible now to do it in foreseeable future for real?
So it depends a lot on the available data. So, if you get like garbage in, garbage out. So the more accurate the data that we put in the system are, the more accurate the simulation is going to be. But this is like very challenging to do. And we are trying to make it as accurate as possible, but there's always the possibility that something is off, or the data were not accurate, or there is some unforeseen variable that it wasn't included in the initial studies where we get the data from. So it's a bit tricky to be. I mean, I cannot be 100% sure of the outcome, but we are trying to do our best, and we're doing pretty good, I think.
Right.
Okay, our next speaker is Dr. Sergey Ushakov, and his talk is titled CALFAD Assisted Thermal Analysis for Water-Free Production. Welcome.
Thank you. Can you hear me well, the mic?
Yeah, it was upside down.
Okay, that's better. Thank you, James. Yeah, I'm really excited to give a talk at this meeting. I want to thank organizers for inviting me to the plenary session. This is my first talk at Mars Society, even though I was a member for 3 years. So my affiliation is at School of Molecular Science here at ASU. School of Molecular Science is a new name for chemistry department, right? Yeah, just to become more embracing. And in our laboratory, our specialty was for 20 plus years, colorimetry and thermal analysis. So that's where thermal analysis comes from. And Richard Otis, co-author of this presentation, is author of the open source Python code for CALFAD. And I will tell you what CALFAD is in a minute. So here is how it came about. And I must say that in this presentation, I will mostly talk about ideas and motivation, because this is not really funded project at the moment, but I hope it will change. So the question which motivates me is, what science do we miss for a sustainable colony on Mars? And for a sustainable colony, I don't mean just have enough oxygen to breathe and food to eat, but if like in Hitchhiker, a Guide for the Galaxy, Earth will get annihilated, will the people on Mars be able to build their own starship and go further? So I put this artist representation just to illustrate that I think it would be more feasible to build using present science to build self-sustainable human colony on the bottom of the ocean because we have plenty of water and we are still on Earth, we have still the same minerals. So I think the first we need the energy, right? For all the processes, we need the energy. It's always a problem on Earth as well. But here I think we have science figured out. So there is a fusion reactors can provide the abundant energy source. And we have supply of thorium for a foreseeable future. There is 4 times of thorium abundance compared with uranium, just because it decays much slower. And it should be the same on Mars. And thorium reactors already being tested in China. And the only reason we used uranium in the nuclear energy program is because it was a byproduct of military industrial complex. The old technology was developed originally to drive submarines and then transfer it. But it doesn't have to be so. And I used the word fission reactors because I believe that we should reserve nuclear for nuclear bombs because the perception is the big issue. Yeah, and there is thorium on Mars, and well, I learned at this conference that this spot actually, maybe from some unknown nuclear event, and it may be surface deep, but it's certainly in different mineral form than on Earth from geological history of Mars. That's what we can say. Well, and here I would like to digress a bit. I'm a mineralogist by training, and during my PhD, I worked on these lavas. And you will not find these lavas on Mars because they're Chernobyl lavas. And whenever I put this slide, it invariably brings some attention, which is the problem. Because if I would say that I worked on the remediation of the industrial accident on chemical plant, that would be routine. And this is the subject for another talk, but personally, I was very surprised that Elon Musk, when he was giving his first presentation on Mars, was very shy to mention nuclear, right? He said, "Oh, maybe we could." And it tells that perception, which doesn't have any basis in the data. So this is the statement from Jaworowski, who was a chairman of the United Nations Scientific Committee on the effect of atomic radiation during the accident. And it was the accident, and what made it a catastrophe was that reaction, which was completely unjustified. So providing we have the abundant source of energy, we can mine the water on Mars from ice. And I believe in next talk, we're going to hear how much ice on Mars, because from what I read, that underground lake mentioned yesterday is still big if. Yeah. But this paper was published by 30 authors from 20 organizations, including Honeybee Robotics. We had a talk from So what struck me, these statements that they're saying surprisingly little new science is required to build this plant. And no human presence is required to operate it. And they even put the cost about a luxury hotel in Las Vegas. So this will not be the bottleneck. But again, the problem, will it give us enough water to bring all the technologies we developed on Earth to make the stuff? And here I just took thorium because I like that subject, right? So how we get thorium on Earth? Well, first, Mother Earth concentrated for us during geological processes by fractional crystallization. Monazite, thorium and rare earth phosphate is one of the first minerals which crystallize from magmas. And then during the million years, by erosion in water, when this we get the beaches with thorium source as a monazite. And then there are two ways to process this monazite: is acid digestion and alkaline digestion. And of course, both of these processes takes copious amount of water and produce waste, and etc. Much more attractive process as a metal oxides electrolysis. Regolith on Mars, these basically metal oxides, just like what we find on Earth. Most of the rocks, these are metal oxides. Interesting part that this paper was presented 1 month before the moon landing, right? So it's not a new idea at all. And with electrolysis, just like you can produce oxygen and hydrogen by splitting the water, you can split metal oxides to produce metal and oxygen. And the reason it wasn't studied before, well, since the reason we don't see a lot of presentations on this, right? Because it requires energy, right? And it was out of consideration that we would have enough energy to melt regolith and to do electrolysis. So the latest work on NASA website from 2006, where they looked into experiments on metal oxide electrolysis, which involved bringing their supporting electrolyte from Earth just to lower the temperature. Well, the beauty that if you really understand this process, you can get not only oxygen, you can get all the metals just varying their current, which you run through oxide melt. So one could imagine that that one can add to this fleet of boats for the water mining from ice, another fleet of boats for fractional crystallization and electrolysis of regolith, which would of course also get all the water, because when you melt regolith, all the water coming out. But then you can get the oxygen by electrolysis, and you can get different metals by varying electrolysis conditions. And if you don't fully melt it, but partially melt it and get the correct composition of the melt by electrolysis, you can design your ceramic and construction materials. However, the problem is that a lot of new science is required for this to happen. I would say it's more new science than for nuclear propulsion. For nuclear propulsion, like we've heard, the problem that, okay, will their nuclear reactor comes up in 6 months after you first fire it, and it's a question of material and engineering, but materials were tested 50 years ago, and it's very specific conditions. So now I want to talk about CalFAD. And CalFAD, it's acronym for calculations of phase diagram. Also, their current practitioners of CalFAD like to name it a computer coupling of phase diagrams and thermochemistry. And it really goes back to Gibbs, Josiah Willard Gibbs, and Albert Einstein called him the greatest mind in American history. And I just, during the previous talk this morning, I realized that when he came up with his functions, that astronomers first saw these channels on Mars. Well, luckily, he didn't die in the Civil War like many of his classmates at Yale. And he was a very modest man. So despite what he did was monumental achievement, he said that the greatest difficulties are in experiment to find the shape of this function. And this labor for metals has been mostly done. And what CalFAD is doing, it's optimizing Gibbs free energy, minimizing Gibbs free energy functions for all possible phases in the given compositional space. And here's the example of on this diagram is an example of CalFAD calculations for 9-component steel alloy, which shows you different phases at different temperature and different carbon content. And how accurate these predictions, these maps, depends on how good databases you get. And this is the work which has been going on for more than 50 years, because metals, of course, are such a critical focus for the human society since Bronze Age. And here I would like to bring this slide just to show how it developed and broad number of the new alloys, and they're designed in a very short time. And the number of tools built on that to deal with kinetics and which use the CalFAD input as a starting point. And I borrowed this slide from Gregory Olsen and Charlie Kuhlman. Gregory Olsen is a thermocalc professor of the practice at MIT. And thermocalc is one of the first programs which start developing these databases 50 years ago. It's actually, I believe, started in Sweden. But and Charlie Kuhlman was his graduate student and working on this CalFAD modeling of the steels. And what Charlie Kuhlman was given a talk at ASU last year, and now he's in charge for material design both at Spaceland, at Tesla and SpaceX. And just to bring the role of CalFAD in the going to Mars issue, that it was critical for designing their Raptor engine and even the hull of the Starship. Well, now I want to talk about thermal analysis. There was another presentation named thermal analysis, and here I want to start with the thermal analysis in engineering and material science have different meaning. In engineering, thermal analysis is to design your heat sinks and flow to provide the given temperature for the components. So in chemistry and material science, thermal analysis most commonly refer to way to detect changes in materials as you heat them. So for example, in this slide, you see that CMOS, calcium, magnesium, aluminum, silicate composition, when you heat it up, you can detect temperature when it crystallizes and temperature when it starts melting. And it's a big field, so there are several societies for thermal analysis and many companies which makes the instruments. And thermal analysis contributed a lot to CalFAT by first providing data for experimental phase diagram constructions and for thermodynamic for the single phases. So in CalFAT optimizations include all this data to produce CalFAT databases. However, you would be surprised that given so many companies working on that and that the field is so old, there are very few databases for thermal analysis. And the reason for that they're not really additive. You cannot tell what the mixture of the oxides will do if you just know the thermal analysis of the constituent oxides. But there is one exception. We have the open thermal analysis database from the Phoenix Mars lander, just because NASA had to disclose all the collected data. Well, unfortunately, there is no thermal analysis instruments on Mars working now on the Curiosity and Perseverance. And the problem with, I think the reason for that NASA scientists had a hard time interpreting thermal analysis data from Phoenix lander, because they had to run a bunch of experiments imitating Mars atmosphere and trying different compositions to match them. So what we did, just as the first experimental effort to develop this science or direction, we did a thermal analysis on the Mars global simulant from Exolit lab. And it's, of course, this simulant, the main purpose of that is to test the rovers, etc. And it represent only what you find on surface. As soon as you start digging, like we've heard, the composition changes. Right? But nevertheless, it's a mineral simulant, and these are constituent minerals here. And from thermal analysis data tell us that it starts melting at 1150 and finish melting at 1450. Right? And we did CalFAT modeling, not with ThermoCalc, with another software which has better database for the oxides, which they call SLUG because it's all related to metallurgy problems. And we can see that the beginning of onset of melting we model pretty accurately, but then curve diverge. So here, the difference, the thermal analysis give us just that heat flow trace, that's all. But the CalFAT modeling, every point in this green curve gives you total full information about state of the system, give you composition of liquids, coexisting solid phases, and their composition. So if one develop in this direction to be able to match thermal analysis of curves of known compositions with those modeled by CalFAT, one can use it to provide that necessary science to engineer those electrolysis boats and to make sure that they can be controlled to produce these materials in different metals. Well, here I need to mention what they call a course of CalFAT, because their standard way how these databases are built, you optimize data for single elements, and then for the binary phase diagrams, and then few ternaries, and then you can work with multi-component system. And this is what they call reverse pyramid of CalFAT, because you have to change everything if you get optimized data for one element. So that was accounted for this very long development of these databases and the fact that they are all tightly guarded by the companies. But just in the recent few years, we have a very great development. It's the open source CalFAT software and the idea that you can use Monte Carlo simulations to have their extendable self-optimizing database builder. So essentially you can feed data from multi-component complex systems such as regolith, experimental data on the melting temperature and other, and optimize everything else to get you predictive power. So we're really excited about that, and the concept is basically to use thermal analysis on known complex compositions together with these CalFAT tools to build these databases and to engineer those rovers at the end. And that's my last slide. The key points that electrolysis and fractional crystallization have the potential to provide the means for water-free mining and production on Mars and beyond. Then CalFAT-assisted thermal analysis can be a tool to provide missing science. And the first step, as I see it, is this creation of open machine-readable thermal analysis databases for CalFAT training on complex oxides. And with this, I will take any questions.
So talking about the CalFAT software, it sounds like it's a work in progress. I've worked with KimCAD, Aspen, all those for years. When you've got good data, they work really great. When you don't, you get way off track. So it sounds like CalFAT's good for some things, but you still need more data for others.
Yeah, absolutely. That's why I showed all this example with CalFAT being used in SpaceX to engineer new materials as they go, because there are not a lot of data on metals, and this was effort of private companies, and the problem of CalFAT in a way that it turned out to be so useful for metallurgists, right? Then it's quickly commercialized, even though it came originally from academia. It started as a free program, and these databases are tightly guarded, and but funding agencies consider CalFAT as as a tool for engineers, and you cannot really get the funding for development of CalFAT databases. But for oxides, there are limited databases for oxides for the thermal barrier coatings, for example. And of course the thermocalc also. I believe they come up with a new database for CMOS, which studied for the processes to come up with the environmental coating, which wouldn't interact with the dust, right? But I hope people who didn't hear about CalFAT now have some appreciation.
Well, Sergey, I applaud you for bringing CalFAT to public light again, because it's obviously an overlooked means of analyzing and pointing the ways to improve means of extraction materials. But I ask you also, have you, of course, thermal analysis is decomposing existing materials, but there's also a new field of plasma chemistry developing, where you bring anions and cations together under laboratory conditions, like Humlet is doing at the University of Gothenburg. Have you looked at that aspect of it in terms of plasma chemistry?
Well, in terms of plasma physics, yeah. Well, I think it's very, very exciting field in terms from materials and chemistry point of view. in fusion, developed fusion reactors, you have their materials which need to meet all the extremes, right? High temperature, high magnetic field. Yeah, but in terms of science, which can be done right now, and from my background, yeah, that's what I see, biggest contribution from for the Mars mission.
Hey, so this is very interesting research, but so this is somewhat outside of my wheelhouse. So I have a couple questions about fractional crystallization itself. So everything that you showed seems to be like the first pass through, like you're taking unmodified regolith and just sending it through here and able to get the different minerals precipitating out here. So the first question for you is, how finite are a lot of these boundaries between the different crystallization states? Are you looking at usually like very pure crystals coming out, or do you end up with some sort of homogeneous or some sort of mix?
Yeah, good question. Yeah, thank you for bringing fractional crystallization, because that's the part which I don't know if it will work or not, right? Because I guess that's the difference with science and engineering. Also, I would say that first law of thermodynamics came of the failure of engineers to build a perpetuum mobile, right? So we really work in tandem. Yeah, because in principle, you can change the composition of the complex melt just by taking the metals out of it by electrolysis, since they go at different potential, right? But in practice, it's really hard to vary this potential accurately enough, because the conductivity in oxide melts, and main problem is the material. So it's easy to get things working for half an hour in a lab. Can you get it working for for a year and still keep working, right? Yeah, so fractional crystallization, geologically, it happens over long times, right? And we use it in different processes to bring the crystals and to purify stuff by fractional crystallization in aqueous solutions. Yeah, but it's one of their things which is not clear if it's applicable or not.
Thank you for bringing this presentation. If you got the funding that you wanted, have you scoped out like what would be the funding, and how long would it take, and how many researchers would be involved, et cetera?
Well, first we were actually applying for the funding just to get more to build those machine readable databases for thermal analysis of regolith simulants, right? And then go from there. Yeah.
Thank you so much.
Thank you.
Okay, everyone, our next speaker is Stefano Nerozzi, and his talk is about the International Ice Mapper mission. Welcome.
Real good. Oh, yep, it works now. Well, again, thank you very much for having me today, especially on a Sunday at lunchtime. And thank you very much to all my colleagues and the measurement definition team for helping me draft this presentation. It was a lot of material to condense into such a short presentation. So IMM, or the International Mars Ice Mapper, is really an international effort where multiple space agencies came together, all with their different main goals in terms of science and exploration of Mars, and came together to form a mission that will address one central item that is in common between all their objectives, which is the search for near surface water ice. That is because you can imagine water ice is essential to make fuel, to provide drinking water for astronauts, for understanding the climate and geologic evolution of Mars, and many other objectives. These space agencies are in this continent: the NASA Space Agency, the Canadian Space Agency in Europe, Italy, and the Netherlands Space Agencies. And in Asia, we have JAXA, so the Japanese Space Agencies. They came together not only to form IMIM as a mission, but also define the measurement definition team. In particular, the main goal of IMIM is to map and characterize near surface ice, which is the accessible ice. With these words, we mean the uppermost 10 meters of the subsurface. That's where we look for ice. This ice will provide the means for future human exploration and scientific endeavors on Mars. The MDT was assembled in order to provide payload definitions and traceability matrices to achieve reconnaissance and scientific goals to search for this ice and beyond. Also make recommendations for any supplemental payload and instruments that may be necessary to achieve the main goal, that is find ice on Mars. And also, finally, very important is to draft a concept of operation for IMIM, that is how the spacecraft and the mission will operate through its lifetime to achieve its objectives. The MDT was a very large team, tens of scientists, engineers, and technical personnel from all over the world. The vast majority of us were competitively selected from our own applications. Those were available to anyone, so anyone could enter an application. And we were selected on the basis of the expertise and the knowledge that we could bring to this mission, and in particular, the search for ice. The executive committees and the leads were selected by agreement of the partner space agencies. Now, the MDT started by following guidelines and assumptions regarding the mission itself. So first of all, there is an anchor payload, a central instrument to this mission that is a synthetic aperture radar operating in L-band, which in this case means center frequency of 930 megahertz, that has polarimetric capability and also is capable of performing side-looking imagery observations as well as nadir-looking sounding observations. The orbiter that carries this instrument would arrive at Mars by 2030 and operate in a similar orbit as previous missions, such as Mars Reconnaissance Orbiter of around 300 kilometers altitude. The baseline mission timeline for this mission is 1 Martian year, or almost 2 Earth years. And mission pre-project activities provide constraints on the mission payload configurations and design for MDT consideration. And if any supplementary technologies and instruments are needed to achieve the objectives, those would need to be strictly necessary to achieve such objective while not interfering with the main payload, that is the L-band SAR. The MDT operated through a series of tasks, 3 in total. The first one being exploration driven, and in particular, the goal was to, again, characterize and map subsurface ice within the first 10 meters in the so-called reconnaissance zone. The reconnaissance zone is visible in the image on the right and is delineated by blue lines. This region is at low to mid latitudes and low enough elevation that would allow human exploration and especially landing those locations while providing a high likelihood of finding ice. The reconnaissance objectives within this reconnaissance zone were divided among 3 different teams that inevitably overlapped in their scope. And so there was a lot of communication while we were working on these objectives. The first one revolved around ice, in particular, trying to answer questions such as, where is the ice and how much is there? What are its characteristics? The second team focused more on the regolith and the overburden and its properties and how to map it. And the third one instead focused on human activities and in particular characterizing potential human landing sites. The second task instead revolved around supplemental science and technologies that would be implemented on the mission. So this is in terms of what additional science can the SAR do beyond the reconnaissance objective that is finding ice. The main payload is really capable of doing all sorts of science. So we were tasked on maximizing the science return of such an instrument. And also, if there are any limitation in the primary payload, the L-band SAR, what are the technologies or additional instruments that are needed to achieve our goals, that is, find ice within the first 10 meters of the subsurface? The third task instead was focused on drafting a concept of operational FIMIM. So again, how the mission will operate in its first year at Mars. So regarding our findings, the very first finding was that we drafted a reconnaissance traceability matrix, which is a tool that we use to define parameters that would be observed to meet the reconnaissance objectives. And on the basis of these parameters, we defined how, like, for example, the resolution, accuracy, and methods that were how these parameters would be measured, and also if the main payload can measure it and how it will do it, and if any models are required prior to starting the mission to actually perform these measurements. Our finding was that the majority of these objectives and these parameters to be measured can be met with the primary payload. These high priority parameters, for example, are just the presence or absence of ice in the subsurface, the concentration profile of ice in the subsurface, or, for example, its lateral continuity, and many other parameters as well. The second finding was that this instrument, and especially the combination of its measurement capabilities, that is polarimetric measurements and nadir looking and side looking sounding and imagery capabilities, are a unique and extremely powerful tool to find ice on Mars. This has been demonstrated before, especially on Earth. For example, here on the right, you can see an image acquired by RadarSat in Tombstone National Park in Canada, where via polarimetry, they were able to identify potential ground ice that is visible in greenish yellow colors. Now, this radar actually works in C-band, so quite higher frequencies than L-band, which means that L-band, being at lower frequency, could even be more powerful in detecting deeper ice. Our third finding was that the core payload has a very high likelihood of finding the ice that is most accessible and easier to utilize by human missions. That is relatively pure ice that is covered by a thin layer of fine sediments, such as the one found by the Phoenix mission, the northern latitudes of Mars, where just with one single scoop, they were able to find relatively pure ice under just a few centimeters of sand and dust. If any other scenarios are present on Mars, so for example, rougher surfaces, thicker overburden, or larger clasts, such as boulders, and if the primary payload can't quite detect the ice there, then additional payloads such as a VHF sounder can come in and complement those observations and find the ice. In terms of supplementary payloads, the MDT identified 2 primary payloads that would complement the main L-band SAR capabilities. Those are a VHF sounder and a high-resolution imager. Regarding the VHF sounder, the idea is that the L-band sounder, the primary payload, is excellent at imaging the very shallow subsurface, so the first few meters at incredibly high resolution, but can't go too deep. While existing assets, and especially SHORAD, the shallow radar that is currently orbiting Mars and acquiring data, can see much deeper, but has an about 20 meters of blind zone. So to fill this gap and look for deeper ice that would be found by the L-band SAR, we thought of a VHF sounder that could really image the ice in this gap. The high resolution imager would be similar in technology to HiRISE, so the high resolution science experiment on Mars Reconnaissance Orbiter. So similar spatial resolution, but of course with the benefit of 15 to 20 years of technological development. And this instrument could provide corroboration for our findings in terms of in subsurface stratigraphy from the L-band SAR, as well as the VHF sounder, by looking at fresh impacts exposing ice, or other steep scarps or other location that would expose the ice. And by acquiring stereo images, that is, images acquired from 2 different points of views, we could construct very high resolution digital elevation models that could help us further constraining the subsurface stratigraphy if it is exposed, or generate clutter simulation that would resolve any ambiguities that we see in our interpretation of subsurface sounding data. In terms of additional science, we found that the primary payload is incredibly capable and can provide a vast array of additional science capabilities that go beyond the search for ice on Mars. So starting from atmospheric science, we could look at the coupling between the surface and the atmosphere. We could do ionospheric soundings as well, for example. In terms of geological studies, we could look at polar processes and other ice-related processes that operate at mid to high latitudes, so outside the reconnaissance zone, as well as achieving a better understanding of the evolution of volcanic terrains and other landscapes that, for example, were shaped by the flow of water, and also examine unique terrains that are still enigmatic, such as the Medusa Fossa Formation that lies at the equator and is still debated whether it is a dry volcanic deposit or if it contains water ice. In terms of habitability, the radar could help locating current and recent past habitable zones on Mars where brines or ice capable of melting may exist currently on Mars. Oh, I forgot to mention that the MDT collected all these additional science operations and measurements that can be done by the primary payload, and built a science traceability matrix that describes how these science observations could be made. The next 2 findings revolve around the additional science and the additional reconnaissance objectives that could be met with additional payloads. So the VHF sounder and the imager not only are an excellent complement to find ice, but themselves can provide additional science to augment the scientific return of the mission. And also, IMEM could further increment its scientific output and meet all the reconnaissance objectives if it included other instruments such as instruments that are capable of measuring surface temperature, performing global measurements of winds, or, for example, obtaining a more complete measurement of surface composition. In terms of operations, the MDT found that the mission could achieve its objectives if it was operated through two different phases. The first phase will be a reconnaissance one, where the spacecraft would operate in imaging mode for at least 80% of the data returned back to Earth, and image most of the surface at a resolution of 30 meters per pixel. The remaining 20% of the data could be allocated for other focused measurements of the surface by the radar imager, or other operations such as subsurface sounding or additional payloads. After this reconnaissance phase is complete, then the rest of the Martian year would be occupied by performing detailed measurements of potential landing sites and other regions of interest that have been identified prior to the mission and during the mission along the reconnaissance phase. In terms of data returned back to Earth, MDT found that the mission can successfully complete its reconnaissance goals and objectives just with the primary payload, and would benefit again from additional instruments, but could greatly enhance its return in terms of reconnaissance and science if the mission had greater downlink capabilities. So there is a plot on the right that illustrates the baseline mode of operation. So one measurement every 4 orbits of the SAR imager in the first reconnaissance phase. And you can see that in 10 months, we can achieve 80% of coverage of the surface of Mars in this mode. But if we had a little bit more downlink capabilities and, for example, operate the instrument in only 1 every 2 orbits, we could achieve the same result in much less time, less than half of the time, and achieve a nearly complete coverage of the surface of Mars and have enough time to perform other activities as well. So our recommendation with the agency is that the agencies should explore options to augment the downlink capabilities of the spacecraft. I will conclude by leaving this link, which is a link to the final report. It's publicly available. It's 200 pages, very rich in details about the entire MDT process from its conception to the final findings. And I'll take any questions. Thank you.
I understand that it's believed that there are ice deposits as deep down as 1 kilometer or more. I would be interested with your instruments, how deep down do you think can you detect ice or water deposits? And if it wasn't for budget limitations, are there other capabilities that exist that are not flying on this spacecraft that you would like to fly if it was affordable?
Excellent question. So it really depends on the nature of the ice itself and its overburden. So, for example, if it is covered by materials that are electrically lossy, you could have very thick ice and relatively pure ice with just a little overburden, but the radar would have a hard time seeing through it. And this would apply to any radar, not just the anchor payload, but even existing radars. And in terms of very deep water ice, the current assets, so SHORAD and MARSES, are the best bet to find that kind of ice. This mission was really conceived to find accessible ice. So ice that can be easily utilized by humans. So ice within the first 10 meters. And even then, like try to imagine digging through just a few meters of regolith, it could be very difficult. So the focus was really the near subsurface, and that is why an L-band radar was recommended. In terms of budget, if we had, in an ideal world, if you had an unlimited budget, we could add other radar imager and other instruments that would just sense deeper. But again, the current assets are probably one of the best bets that we have in identifying very deep ice or any liquid water, really. Because mainly as you go up in frequency and the current assets are relatively low frequency, the penetration depth capabilities decrease. So we should really focus on using our current assets rather than bringing new instruments that probably couldn't really augment the scientific return too much.
Hello. Do we have idea about the salinity and concentrations of the salts in those close to surface ice deposits?
So that is actually one of the findings of the MDT in terms of models. So one of the, I'll bring up my slides. I don't know if can you see my cursor? Maybe not. But if you look at the ice presence and concentration and some other objectives that we found in our reconnaissance traceability matrix, there is one element for ice salinity.
You have a laser pointer there.
Oh, okay. It was mostly for the people online, but yeah. So there is, for example, non-ice constituents in the ice matrix. So, for example, solutes in ice or the ice matrix that would contain, for example, that would include salts. So in part, we know what to expect in known icy deposits on Mars based on current and past observations. And if any new observations need to be made by the anchor payload and the additional instruments, there are models that we found would need to be developed or further enhanced to achieve a better understanding of what kind of salts we might find in the ice.
Apologies if I missed it, but when would this mission be approved if it gets approval?
The notional indication that they gave us is that the mission would arrive at Mars before 2030. Honestly, personally, I don't know anything beyond that. We only the information we know in terms of approval of missions or budgets or anything. We know what you know. Everything is public.
So hello, very interesting study. I'm interested to read the report, but I was wondering if you could tell me what the minimum concentration of ice that you guys would be able to resolve and like the minimum difference you could resolve with the LBAN radar.
Excellent question. That again depends on the ice, the characteristics of the ice itself, how deep it is, and how much and what kind of regolith is on top of it. So if the right condition exists, especially the polarimetry capability of the SAR in imaging mode could really identify even very small concentration of ice. This has been demonstrated, for example, on the moon for the polar deposits from ground radar observations, where they found ice concentrations that were then later revealed, for example, by the LCROSS mission to be apparently relatively small. Now, I don't remember the numbers, but if the right conditions exist, the ice concentration could be relatively low and would still be identified by polarization.
Thank you. I have a follow-up question on the timing and decisions on moving forward. I understand there was a budget proposal this fiscal year for NASA to pull out of this project. Where are we on that decision? How would that affect the timeline? We have the slogan "Humans to Mars" this decade. It'd be great to get the ice mapper out there before the humans arrive.
That is an excellent question, but I don't know anything anything beyond what you already know. We were not given any information about budgets or upper level decisions on these missions. We were only tasked to define measurements that this mission would make. We don't know anything else.
The high-rise results were publicly posted on the internet. Will the data from this be available in the same kind of worldwide fashion?
That depends on what the partner agencies will decide with this mission. This was not something that was tasked to the MDT. So the answer is I don't know. It really depends what the partner agencies eventually decide for the mission. Well, thank you.
Maria, are you able to hear me?
I am.
Can we do a quick sound check? Say something
Sure.
else?
Hello, hello, hello.
Okay, awesome. Would you like to share your slides? Make sure those come up
Sure.
okay.
Let me,
And then I will introduce you.
great.
Okay, perfect. You're looking good.
Okay, great.
All right. All right, everyone. Our next speaker is Maria Tanner, and she's with Star Harbor Academy. Welcome, Maria.
Hi, thank you, James. Really excited to be here and speak with you all. So appreciate the invitation. I'll share a bit about myself quickly. I feel like my story is, sort of relevant to the topic today, which is, what are the new pathways to space that are emerging? So my name is Maria Tanner, and I'm not gonna spend too much time on myself because really, we're here to talk about you, your sisters, brothers, nieces, nephews, parents, children, friends, neighbors, colleagues, and all the opportunities that are beginning to open up, for the non-traditional astronaut. So I'll start by saying space has always been my thing. I honestly can't remember a time when I didn't have my eyes on the sky. And I always wanted to be an astronaut. And when you're a kid saying you want to be an astronaut, people are excited for you and they believe with you and, go get it. And then you start to get a little bit older and the message starts to change. Well, there's only a few people that get selected, so you better have a plan B. So I found when I went away to university, instead of pursuing that path, I got sidetracked for a little bit with a degree in political economy of industrial societies. But in my senior year, I was really struggling and my mom said, Mariah, what are you doing? Space is your thing. You really need to be doing that. So I researched my options and that day I switched to becoming a physics major. Didn't really know anything about it, had never taken this physics class, but fortunately it was the best decision I ever made. And so I was, PhD bound because at the time there were really only two pathways into becoming a NASA astronaut. You could be a military pilot or you could be a PhD scientist. And so that was my plan. But just before my graduation, I was offered a job at TRW, so now I'm dating myself. Now Northrop Grumman Space Technology. in Redondo Beach to work on a really fantastic NASA telescope called SIM, space-based interferometry mission. And my would-be boss said, you know, the lead engineer is likely going to get to fly with the telescope on the shuttle. And so like it was like this epiphany occurred, you know, wait, I could go to space without getting my PhD. Done, sold. You know, I mean, unfortunately, that telescope died with the shuttle program, but the net effect was that it opened my eyes to the idea that maybe, just maybe, there were going to be other pathways to getting to space. And so I started paying attention to what was going on in the commercial space arena. I volunteered with X Prize, cried the day that Scaled Composites, now Virgin Galactic, won. Felt like a new day was dawning. And then I became a flight crew for Zero Gravity Corporation, and got hundreds of parabolas under my belt. Really got to see the research that was being done and saw that no one was really thinking about training. So we put together a phenomenal team and have been working on it for the last number of years with two primary intentions. One, to create access and more diverse access for people to get to space. And then additionally, how can we leverage the enthusiasm and resources that are being applied to space, especially now, towards making life better at home? So, slides, there we go. So today, you know, progress is being made towards greater access, slow though it may be for some of us. But I would say it's still not great. You know, there aren't a lot of flights occurring, and those that are occurring, you know, are still generally government or with paid access, you know, requiring quite a bit of capital. So, you know, the current pathways, I'm sure everybody's familiar with, you know, we have the traditional NASA government space agencies, commercial spaceflight participants, the pay to play, or win the lotto, we've been calling it. You know, you can be gifted a flight or a contest winner, you know, which is, I would say, the most likely access right now for those that don't have millions of dollars to put towards the space flight. Actually win the lotto. Soon, and this work is being done right now, is the commercial professional crew, operators and payload mission specialists, you know, not very different from what occurs right now. Their former NASA government astronauts will be making up initially, especially, you know, a large segment of this population. But there are, you know, we're in conversations with virtually all of the commercial space station contract winners and folks that are looking to put people in space. And we know that there are going to be privately trained staff astronauts that these companies are going to be hiring. I would say there's probably not a lot of change for this category of astronaut. You know, again, we're looking at pilots, scientists, engineers. These folks will be fully versed in station operations, can manage diverse crew and passenger dynamics. And similar to on-ground researchers being able to hire NASA astronauts, these professional crew will also, or those companies will be able to be hired to perform work and experiments on board. Some of the things that are happening that are new is these commercial private crew and private sector employee opportunities. So there will be privately trained mission specific astronauts. These will be coming from a variety of industries. These could be researchers that are selected to conduct their own research on board the station. You know, traditionally, there's been, you know, a number of challenges for researchers on the ground. One is they have to really understand the environment that they're designing their experiment for. And often, there's a not negligible percentage of experiments that do not generate the data that they're hoping for because the initial design was inadequate in one way or another. And so one of the opportunities when you're sending the scientists themselves is they can make real-time adjustments on the fly. And so that's of extreme interest to a lot of industries that we've been speaking with. Likewise, the time it takes for data to get from the station processed into the researchers traditionally has, could take weeks or months. Now, as of, I believe this year, that has been increased, down to hours because of some onboard processing that's possible. However, it's still not a substitute for scientists being able to be there and manage their experiments themselves. So that's one area that we see a lot of interest. Pharmaceuticals, biotech, agritech, energy, the list is actually quite long. And encompasses, research NASA is not interested in. There's a lot of research that either doesn't apply for grants in the first place or gets rejected because it's not a topic that NASA is interested in looking at, but the private sector may be. Company proprietary research, as I mentioned, real-time adjustments, space medicine, the possibility of doing human studies in space really hasn't been a thing, and there's all kinds of issues and ethics involved with that, but that's something that is definitely being looked at. Likewise, the entertainment industry. If there was a film crew who has been trained to operate in space, that time is going to be more effective than if studios try and bring up their own camera folks, for example. And so that's a conversation that's occurring. In space manufacturing, engineers, technicians, machinists, also education, teachers, students. There was a call with NASA earlier this week where the question came up, what are the policies going to be related to, sending teenagers? And, it's a whole new world. This is not something I think NASA has really considered before now. So that's all being looked at. So one of the things that Star Harbor is doing that we're really, really excited about is, we're creating this incredible facility, Boeing 767 for parabolic flight, very, very large pool, neutral buoyancy tank, high gravity centrifuge, hypobaric chambers for high altitude, low pressure, low oxygen environments, hyperbaric chambers for pool safety primarily, but also some research, space sim lab, human performance center, land-based and underwater habitats, and for long duration mission training. And one of the things that we're really excited about is, we're creating this trainer astronaut internship. So we'll be hiring folks to come in and, with relevant backgrounds to become trainers for Star Harbor. In that process, we'll be learning all there is to know about, all these various environments, get trained up themselves, station specific and vehicle specific training, depending on where they're looking to go afterward. And then at the end of right now, it looks like it's going to be about a 3-year period. And this is an employment position. So you're getting paid instead of having to go and pay hundreds of thousands or millions of dollars to get this training on your own. You'll be able to get hired as a trainer, go through this program, and at the end of 3 years, be certified to fly and can actually apply for one of those professional crew positions that I spoke about earlier. One of the other things that has really struck us, and it was really reinforced on that call this week, is the medical standards that NASA has for NASA astronauts. You basically have to be a perfect human specimen to get selected. The number of disqualifying criteria is extraordinary. Now it's different if you've been selected. They had a fix it and fly them policy. So if you've been selected and they've already spent money on your training and your education, they will do whatever they can to keep you flying. But to get selected in the first place, it's a very narrow bandwidth of the folks that will qualify. So, some of the questions that we're asking, and we're fortunate to be working with a lot of really, really talented individuals and institutions. We have an MOU with Anschutz Medical, just signed with National Jewish Health. We're talking to UTMB, University of Texas Medical, and a number of other institutions that are really wanting to look at, what is really safe to fly? Do you have to be that perfect human specimen to be effective in space? The follow-on question to that is, then what changes need to occur within the vehicles in the station if you're going to have a broader spectrum of folks present? Because right now the medical capability on ISS is there is some, but it's really not set up to handle major events. So when you broaden that spectrum, what new capabilities and resources do you have to have on board? And that's a question that we're getting answered, and a lot of very, very interesting discussion is coming out of that. Also, educational minimums. Do you have to have a master's PhD? What are the knowledge and skills that are really needed to do that job? Is it necessary to be trained for every eventuality, or can new standards be set that are, I don't want to say good enough, but good enough, because the commercial industry is not going to have the tolerance for 3 to 4 years and $15 to $20 million to train folks to live on the stations. But how low can we lower that bar and still ensure safety and effective results? So I ran through that pretty quickly, so I wanted to make sure we had time for questions, and happy to answer any you might have.
Awesome. Thank you so much, Maria. Are there any questions?
Right. Thank you so much for your work. It's very important and groundbreaking. Hopefully some of that will be on Mars one day. And my name is Bill Gardner, by the way. And the modern health science is advancing so quickly. What do you think of the new discoveries about insulin resistance, hyperinsulinemia, and insulin sensitivity as an overlooked or recently found element of health that is affecting the astronauts already?
Interesting. So as I mentioned, I'm a physicist, not a doctor, but we have been having conversations with a number of space medicine doctors, and also folks that work in the different abilities space. So meaning, people that aren't just maybe dealing with diabetes and blood issues, but also maybe are in a wheelchair or have prosthetics. What are the accessibility parameters that the new stations and new space vehicles can accommodate, so that we can really broadening it up to as many people as possible. And so that's, in fact, it was interesting on the call with NASA earlier this week. There was a lot of conversation about diversity and bringing greater diversity to the commercial stations. But the sort of underlying subtext, which I thought was interesting, was that the assumption was that everybody was still fully enabled. And I apologize if I'm getting the terminology wrong. I'm not meaning to be offensive to anyone. Because there's a huge population of individuals who'd be interested in traveling to space that, because of physical limitations, are currently barred. And does it really need to be that way? So, I think there's a number of, especially the very common conditions, like you mentioned, diabetes, those rates have been, skyrocketing over the last few decades. So if we have conditions like that, they're automatic excluders. There's a lot of people good people that could be flying that probably won't. So yeah, I do think that there's going to be a lot of effort put into solutions.
Hi, Mariah. My name is Gary Schneider from the University of Colorado Health, biomedical engineer over there.
Great.
I just want to say thank you so much for your talk tonight. It's been amazing to hear how far you guys have come. I've been in contact with Aaron Bonilla from your facility several years ago, and you guys have just skyrocketed in such a short amount of time. So I guess my question for tonight is, you had mentioned the trainer astronaut internship program. What would be the best way to get involved, both for myself as an engineer and someone studying it, but then also for our amputee population out of University of Colorado Health? We have some folks in the OI program that are really interested in working with you guys.
Oh, fantastic. So I would say, right now, my best suggestion would probably be to reach out to me on LinkedIn, or Shabam Garg would also be a good one, which I think if you go into LinkedIn, you'd probably be able to find him, and send a message. If I get a random connection request, then often I will ignore it. But if it comes with a message, then I always respond. And we'll be keeping a short list when it comes time to hire, which I believe we'll be looking at. So as far as our schedule goes, we signed the proper purchase sale agreement for the land last October. We're currently in the architectural engineering design phase right now. We're expecting to put a shovel in the ground. Probably first thing, we're going to be located just south of Denver. So after the thaw in the spring. And then we're looking at about 2.5 to 3 years construction. And then we'll be doors open, but we'll be hiring the trainers probably about a year before that. And in the meantime, there may also be opportunities to get involved in the curriculum creation, depending on people's areas of specialization.
Very cool stuff. Thank you so much. On the parabolic flight opportunities, there's currently a couple of providers on that, but their prices are fairly high. When you look at that market, is it the kind of thing that if you can have the price, you get 10 times the customers, or what do you see the opportunities there?
Yeah, I have to be careful what I say, because I absolutely support zero gravity, and they've done an amazing job for the last years providing these experiences for people. I think there are a number of ways in which we'll be able to create a really dynamic experience, and more importantly, one of the opportunities, we filed a patent about a year and a half ago, I want to say, that will take the cost for a medium-sized, to small payload for research purposes, down from the tens of thousands to about $1,500 to $2,000, because we'll be able to fit many more of them on board any given flight. So, I like to say this puts microgravity research in the realm of a PTA raise. This can make it available to high school groups, university students. It no longer has to be something huge that requires massive amounts of grant funding to participate in. This is something that kids and their PTA organizations will be able to participate in, and or researchers that before could only afford to maybe do one flight or maybe two, now could do dozens, and engineers could iterate on their designs to make sure that they're ready to roll before they actually end up with a launch date. So it's pretty exciting, some of the changes that are coming. Yeah, I see one question. What adverse health conditions are actually beneficial for a space mission? I don't know, but that's a really interesting question. I will look into it. Yeah, I'm not sure if there are any, but I will talk to our folks and find out.
Any other questions? Okay, thank you so much, Maria. We really appreciate you joining our conference today.
Yeah, you bet. All right, have a good one.
All right. Okay, folks, so before I bring Robert up for his closing remarks, I wanted to tell you about a really cool opportunity you all have. We're about to hand you out a little red envelope, and inside it is a postcard from Blue Origin's Postcards from Space program. Now, the way this works, we've received a lot of these to give out to our attendees. And so the back is blank, the front has a space for an address and a stamp. You can draw whatever you'd like or write a message on this, whatever you'd want to do on the blank area. And then you put your own address on this and a stamp, and you stick it in an envelope, which we've conveniently provided for you. And you can mail it to Blue Origin. The address is on the postcard. And this will fly in a New Shepard flight, and they will mail it back to you. It's called Postcards from Space. And so take advantage of that. Now, for folks of you joining us virtually, we are distributing these through our chapters. So find your local chapter and go to one of their meetings. And if you don't have a local chapter in your area, this is a great opportunity for you to form one. And we'll send you some of these postcards to distribute at your events. Okay. All right, and our last speaker of the day and of the conference is our founder and president, Dr. Robert Zubrin, for his closing remarks.
Okay. Have to bear with me because I'm trying to work through a number of thoughts. But as I said last night, we're at a time of crisis and opportunity. We have the official space program is very confused. There's new potentials emerging in terms of the new space industry, showing a lot of potential, although some of its leaders are very confused. And we have a world situation which is extremely turbulent. we have a certain vision of the human future. It's an unlimited future. Okay. It's a future in which we see humanity as living not at the end of history, but at the beginning of history, truly at the beginning of history. Okay. That we will be admired by future generations, not because of the magnificence of our civilization, but because we are able to rise above our barbarism. Okay, that is why. Okay, just as you can look at the paintings in the cave in France left by Cro-Magnon people 40,000 years ago and see these were humans, these were capable of art. And you can look at the Gothic cathedrals and say, even though you know of all the barbaric aspects of medieval culture, that these people had high ideals, that they were able to rise above the limitations of their time. Okay, and this time will be remembered by the future as a barbaric time, but also hopefully look back in wonder, okay, that we were able to rise above it and lift humanity out of it. Okay. Now, the issue is fundamentally this, okay? Are human beings consumers of resources, or are we creators? What is the nature of man? Okay. And it affects the entire view of what is necessity and what is practical. Okay. An opponent of our view, Adolf Hitler, once said, encapsulating the other position very well, said, the laws of existence require unlimited killing so that the better may live. Okay, that's a quote. And actually, some people may be interested. It's what he said when he signed the order for the extermination of the city of Leningrad, okay, which they were not successful in doing, but which they wanted to do. But this view is wrong. Okay, it's not just morally wrong, it's wrong from a practical point of view. Okay, because in fact, the human race is not, as the anti-humans would claim, a group of nations, tribes, whatever you would call us, in a war for existence over limited resources. Okay, that is their view, which necessarily entails war. Okay, it defines all other nations, and actually even all other individuals, but humans band together so that they can win these fights. But so all other nations as enemies of every other nation. Okay, so war is implicit in it. Okay, and this point of view was responsible ultimately for all of the major catastrophes, human-caused catastrophes of the 20th century, including the 2 world wars, the Holocaust, the Holodomor, so forth. And it's threatening human existence now. Okay, now it's wrong because in fact, the human race is not a bunch of tribes in a struggle for existence over limited resources. We are diverse families of people, a very disorderly family to be sure at this point, but nevertheless, a family engaged in a joint project to expand the horizons of humanity. Okay. The current leader of China and his close friends think that the United States is their enemy. The West is their enemy. But in fact, the reason why China has developed incredibly, exponentially, 2 orders of magnitude increase in the standard of living over the past 30 years, 100-fold, okay, is because of inventions made in the West, including things ranging from that to this, okay? Electricity, railroads, automobiles, aeroplanes, computers, internets, all this, okay? And yet, okay, it is a fact that the West itself achieved its renaissance because of inventions like paper and printing that were made in China, okay? Inventions made anywhere ultimately become used anywhere. So the creative potential of all nations benefits all nations, okay? This is a very important difference between human social evolution and biological evolution. Human social evolution is not Darwinian. We certainly evolve, but not by superior nations exterminating inferior nations, okay? There's a fundamental reason why that is true. It's because humans can inherit acquired characteristics, okay? And not only from their parents, but from people to whom they are unrelated, acquired characteristics being things like inventions, okay? That's an adaptation that can be arrived at somewhere and then be utilized not only by that person's children, but and even people they know, but by people far away. So we're all in it together, but that is not seen, okay? Now, the conversation at my table, I was sitting next to the gentleman from Blue Origin last night. He referred tangentially to it actually in his remarks, okay? Because he was a believer that the population explosion threatens humanity. That when he was born, there were 4 billion people and now there's 8, and that's a problem. When I was born, there was 2. And if we had made sure there couldn't be 4, maybe he wouldn't exist. Now, and you see, he's wrong. Okay, we're not threatened by there being too many people. We're threatened by people who think there are too many people. Okay, right? You know, that's who threatens you. But we're threatened by and I'm not here arguing for population growth. That's not my point. Okay, my point is that the point of view that additional people are a minus to you, that point of view is a threat. Okay, it's a threat, and not just to them, but to you and to everybody else. Okay, the point of view that there are other nations is a minus to you, is a threat. It is the primary threat facing humanity today. It is the primary threat. Now, I will tell you, though I do not believe in some of the alarmist projections of climate activists, I believe global warming is real. I think it's an issue. I think we're going to have to deal with it. Okay, but it doesn't threaten to kill you this year or next year, okay, or 20 years from now. It threatens to create climate changes that could be harmful in some places and probably beneficial in others because part of the world's too cold. But sure, it's got to be dealt with. But that's not the thing. The main threat to humanity today is that it will kill itself over the belief that other nations are enemies. And you see, and if you believe that other nations are fundamentally enemies and that to whom you're going to have to fight it out sooner or later, then the only question is sooner or later. And by definition, it will be better for one side or the other to do it sooner. Okay, always going to be. Okay, so, and you know, 1912. General Friedrich von Bernhardi, chief intellectual, German general staff, said, look, here's Eurasia. Either we Germans are going to get it or the Russians are going to get it. We're going to have to fight it out with them sooner or later. Okay, sooner or later, let's make it sooner because they haven't industrialized yet. We can take them down now. Okay. Japan and China, 1930s. Who's going to get Asia? Japanese said, let's take them down now while they're weak. So forth. And here you have this now. Putin has defined the West as an adversarial interest. Okay. And actually, from his point of view, given Russia's declining population and so forth, he's not so sure he wants to wait. He wants to position himself. It's completely adverse to Russia's actual interests. Russia's actual interests are to join in the prosperity of the Western world. Poland and other Eastern European countries that have tripled or quadrupled their standards of living since the fall of the Soviet bloc. But anyway, there is that. Now, I actually believe that this particular thing we're seeing now will be rebuffed and contained. Okay, I think that this one, we're going to get through this one. But the next one is going to be more serious. I happen to know that there are people in the American national security establishment who believe that war with China is inevitable. Why? Because there's 1.4 billion of them. That's 10 times as many as there are Russians. And if they all start driving cars and stuff like that, there won't be enough oil in the world. And you can bet your bottom dollar that they have counterparts in Beijing who look at this problem from the opposite side of the chessboard and think comparable thoughts. Not enough for both of us. There's only so much to go around. But that's not true. Okay, it's not true that there's only so much to go around. Now, we've got some time with that one. Those people are more patient than Putin. And in fact, they've got good reasons to wait because they're doing pretty good playing the game under peacetime conditions, by and large. But one way or another, if that point of view prevails, that there will be war. Okay. Now, we have to make sure that point of view does not prevail. That's what this is. This is a battle of ideas. We are engaged in a battle of ideas. Getting humans to Mars, yes, it's for the science. Yes, it's for the challenge. Okay. Yes, it will do wonders for the younger generation in terms of being a part of a society that has that kind of positive view of what it can accomplish and that they should develop their minds so they can be part of it, so they can be leading it. Okay, and that's what we saw with this education initiative, and we want to bring that home. But there's something else here. It's to prove a point. It's to win this battle, this war of ideas. Because you see, if you can see, as I said, there's no such thing as a natural resource. There's only natural raw materials. Mars is a barren place right now. But if human ingenuity is brought to it, it can be the home of many new, thriving, glorious cultures and nations. Okay. Now, that part of this mission is a little beyond our time. But if we can bring it into view, okay, if we can succeed in getting humans to Mars, so then that future, okay, we won't be in it, but we'll see it. Okay, people will see it. It will be understood. that there's a different kind of future, that there's a future of unlimited resources, and there's room enough in the universe for lots of flags, our flag, Chinese flag, Russian flag. Okay, there's universe in there. And not only that, but by using our talents, we can create planets. I mean, Mars is there as a planet, but it's not there as a living planet, not now. I mean, yeah, there's probably bacteria in the groundwater on Mars, and there's a lot of science to be learned by studying them. And, you know, if that's how we get Queen Isabella to provide the jewels for the ship, that's great. But there's more in the New World than a spice route to India. Okay, much more. There's a new world in the New World. Okay, and the you know, that's the thing. That is to if we can get people to Mars, we will show there's no point killing each other over provinces when by working together we can open planets. And if okay, now Mars Society, we actually do have people in Russia and China and so forth, but mostly we operate in the West. Okay, we are really a phenomenon of Western culture, but Western culture is heard, it's watched. Okay, you know, I don't know what it is now, but I was in Russia not too long ago, and you could go into the bookstore and buy Harry Potter. No, and you could watch The Simpsons on television. Okay, our Western ideas do get around the world, and if people here have that kind of view of the future, people there will pick it up. And then if their leaders still want to go on these insane adventures, they will say, why are we doing this? Why are we doing this? Why are you doing this? You know, this past weekend, Xi, the dictator of China, purged some of his leading rivals, or not even really rivals, just people who weren't his stooges within the Communist Party. Okay, the guy who was the previous prime minister of China was dragged out of the Communist Party plenary meeting. Okay, that makes him temporarily stronger, but it's really a demonstration of weakness. Okay, that shows that he feels he cannot even trust other Communist Party leaders to back him in things that he wishes to do. That's what it shows. And so, you know, there's plenty of people of goodwill in these countries. And what we have to do is promote a vision of the human future that makes those who believe war is necessary, that view appears absurd. Okay, we got to make it absurd. We got to make anti-humanism absurd. So anyway, we've got these projects that will spread the vision. Okay, the education project, the Mars stations are going to have additional ones in Mongolia. We're going to have, we're looking to do a mission at the Flashline Mars Arctic Research Station next summer, which should also get a lot of press. There's the rover competitions, but ultimately, you're the messengers. Spread the word in any way you can. That's our goal. We're going to make war absurd. We're going to make it understood that humanity can have, indeed, an infinite future, and that we are not living at the end of history. We're living at the beginning of history. We're present at the creation. And people who join in this vision have an opportunity to be among the creators. Thank you. All right. See you next year, quite possibly right here.